Look up at the night sky. For a moment, forget everything you think you know. Out there, beyond the faint glow of city lights and the familiar patterns of constellations, lies a canvas of pure mystery. We've sent probes to the edge of our solar system and trained unimaginably powerful telescopes on the deepest reaches of space. And with every new observation, we're not just finding answers, we're uncovering questions we never even thought to ask. The universe, it turns out, is far stranger, more whimsical, and more wonderfully bizarre than we ever dared to dream. It's a place where the rules of physics seem to bend, where cosmic objects behave in ways that defy all logic, and where every new discovery feels like turning a page in the greatest sci-fi novel ever written, except it's all stunningly, beautifully real. Today, we are living in a golden age of cosmic revelation. Astronomers and powerful new observatories are now collecting so much data that our map of the cosmos is being redrawn almost weekly, revealing a menagerie of celestial phenomena that are leaving even the most seasoned experts utterly perplexed. We're talking about objects that shouldn't exist, signals with no clear source, and structures on a scale so vast they challenge the very foundations of modern cosmology. This is not just incremental science, this is a paradigm shift happening in real time, and it's inviting all of us to be a part of the greatest detective story in history, a story written in starlight and shadow. So get ready to have your mind expanded, because in this video, we're diving headfirst into 30 of the most jaw-dropping, recently discovered space oddities that are currently baffling scientists and reshaping the entire field of astronomy. From stars that flicker in impossible ways to ghostly radio whispers from the void, we're about to embark on a tour of the cosmos's greatest hits of weirdness. This journey will take us to the very frontiers of human knowledge, to the precipice of understanding, and perhaps even a little bit beyond. So, make yourself comfortable and let's explore the unbelievable together. First on our list is a discovery so profound that it has astronomers openly questioning the very timeline of our cosmos. Imagine finding the fossil of a fully grown, modern human in rock layers dating back to the age of the dinosaurs. That's the scale of the paradox we're facing with what some are calling universe breaker galaxies. Using the phenomenal power of the James Webb Space Telescope, scientists have peered back to a time when the universe was only around 500 to 700 million years old, a mere infant in cosmic terms. Conventional models of galaxy formation tell us that this early in the universe's history, we should only see tiny, nascent galaxies, little more than chaotic clumps of stars and gas, slowly merging over billions of years to build the majestic spirals and ellipticals we see today. But that is not what Webb saw. Instead, it spotted enormous, fully formed, and incredibly massive galaxies, already seemingly old and mature. The sheer scale of these systems is staggering. Some contain the mass of hundreds of billions of stars, a level of maturity that, according to our best calculations, should have taken many billions of years longer to achieve. It's as if the universe skipped its awkward teenage phase entirely and went straight to a settled middle age. The problem this creates is fundamental. Our entire understanding of cosmic evolution, from the Big Bang to the present day, is built upon a framework that now appears to have some gaping holes. How did these colossal structures assemble their mass so quickly? What physical processes, currently unknown to science, could have accelerated star formation and galactic growth at such an unbelievable rate? The existence of these galaxies doesn't just add a new piece to the puzzle. It suggests that the puzzle we thought we were solving might be an entirely different picture altogether. It forces a re-examination of our most basic assumptions, from the nature of dark matter's role in cosmic scaffolding to the very first moments after creation itself. This isn't a small adjustment, it's a potential revolution brewing in the data, a quiet challenge whispered from the dawn of time. While those early universe galaxies challenge our cosmic timeline, another discovery is shaking the very foundations of how we understand the universe's structure on the grandest of scales. Picture, if you will, tracing the positions of distant quasars, the incredibly bright cores of active galaxies across a vast swath of the night sky. This is precisely what a research team was doing, painstakingly mapping the locations of these brilliant beacons when they noticed something that at first seemed like a trick of the data. But it wasn't a trick. They had stumbled upon a formation so immense, so seemingly deliberate in its shape, that it defies easy explanation. Dubbed the Giant Arc, this structure is a near-symmetrical, crescent-shaped curve of galaxies, galaxy clusters, and immense clouds of gas, stretching an almost incomprehensible 3.3 billion light-years across the cosmos. To put that unfathomable size into perspective, if you could hold it in your hand, it would span the length of about 35 full moons in our sky. This isn't just a big object, it is one of the largest single entities ever identified. The profound challenge it presents is rooted in a cornerstone of modern cosmology known as the cosmological principle. This principle is a fundamental assumption that, when you look at the universe on a sufficiently large scale, matter should be spread more or less evenly in all directions. It's the idea that there is no central point, no special place, and no cosmic structures so huge that they make the universe look lumpy and uneven when viewed in its entirety. The cosmological principle suggests that if you were to take a cube measuring 1 billion light-years on each side from anywhere in the universe, the amount of matter inside it would be roughly the same. Yet here we have the Giant Arc, a single, coherent structure that is, by itself, more than 1/10 of the observable radius of the entire universe. A structure of this scale simply should not exist if our foundational principle is correct. It's like stirring a cup of coffee with cream, and instead of it blending into a uniform tan, you find a perfect, swirling pattern the size of the cup itself. It suggests the mixing isn't complete, or that there are forces at work we haven't accounted for. The discovery has naturally ignited fierce debate within the cosmology community. Skeptics rightly question whether the arc is a true physical structure or merely a chance alignment, a statistical fluke in the way galaxies are distributed, much like seeing the shape of a bear in the random stars of a constellation. The researchers behind the discovery, however, have run extensive statistical analyses and argue that the probability of such a symmetrical and coherent structure forming by pure chance is exceedingly low, less than 1%. This has forced cosmologists to confront some truly radical possibilities. Perhaps the influence of dark matter and dark energy, the mysterious components that make up most of the cosmos, is not as uniform as we thought, and they are somehow sculpting matter into these vast filamentary structures. Or maybe, and this is an even more profound thought, the Giant Arc is a fossilized imprint from the universe's very first moments, a relic from a period of rapid inflation that left permanent wrinkles in the fabric of space-time. Whatever the explanation, this colossal arch in the heavens serves as a humbling reminder that our maps of the cosmos are still very much works in progress, and the universe may yet be filled with giants we are only just beginning to see. Now, let's shift our focus from these impossibly large structures to a dramatic and solitary escape artist, a runaway supermassive black hole. You might picture a black hole as a stationary, insatiable monster lurking at the center of a galaxy, and for the most part, you'd be right. But astronomers using the Hubble Space Telescope have caught one in the act of a spectacular galactic getaway. They observed a supermassive black hole weighing as much as 20 million of our suns, not sitting placidly in a galactic core, but instead hurtling through the emptiness of intergalactic space at a staggering speed of over 5 million miles per hour. That's so fast it could travel the distance from Earth to the Moon in under 15 minutes. And what makes this discovery truly mesmerizing is the brilliant, contrail-like streak of young, blue stars it has left in its wake, a luminous scar across the cosmos that tells the story of its violent expulsion. This incredible phenomenon is almost certainly the result of an epic celestial dance that ended in a cosmic slingshot. The most widely accepted explanation involves a cataclysmic merger between three galaxies. In the chaotic final act of this merger, their central supermassive black holes would have begun a gravitational tango, swirling ever closer towards each other. When two of them finally collided and merged, the event would have sent powerful ripples known as gravitational waves shooting through the fabric of space-time. Now, if this merger was asymmetrical, meaning the waves were ejected more strongly in one direction than the others, it could have acted like a rocket engine, violently kicking the newly formed single black hole clear out of the galactic core. But the story doesn't end with the black hole's ejection. As it was flung outwards, it would have plowed through the dense clouds of gas and dust surrounding its former home. The immense gravitational pull of the speeding black hole would have compressed this material, shocking and heating it just enough to trigger a firestorm of star formation directly behind it. Think of it not as a trail of destruction, but as a cosmic plow, tilling the fertile gas and leaving a spontaneous garden of newborn stars in its path. This challenges our static view of black holes and reveals a much more dynamic and influential role they can play, not just as destroyers, but as unlikely creators, seeding new stellar populations across the intergalactic void. Just when we think we're getting a handle on the cosmic rulebook, the universe unveils something that seems to rewrite it entirely. From galaxies that matured too quickly to a runaway black hole seeding stars in its wake, the cosmos is clearly full of surprises. But now, we encounter an object that is perhaps the ultimate cosmic ghost, a galaxy that is, for all practical purposes, invisible. Astronomers have given these phantoms a fittingly mysterious name: dark galaxies. Imagine pointing the most powerful telescopes we have at a patch of sky, collecting light across various wavelengths and seeing almost nothing. Just a faint, diffuse smudge, a wisp of cosmic fog. Yet, when you study this seemingly empty region with radio telescopes and analyze the motion of the tiny amount of detectable hydrogen gas, you find something astonishing. That faint wisp is moving at speeds that indicate the presence of a gravitational force far greater than the visible matter could possibly produce. You are not looking at a small, insignificant cloud. You are looking at the silhouette of an entire galaxy, one dominated not by stars, but by the invisible grip of dark matter. The discovery of objects like Dragonfly 44 was a pivotal moment in this search. Located in the Coma galaxy cluster, this ultra-diffuse galaxy appears incredibly faint and sparse, containing only about 1/100th the number of stars as our own Milky Way. If you were to fly through it, the space between its few, lonely stars would be vast and dark. But when astronomers measured the velocities of those stars, they found they were whizzing around at tremendous speeds. The gravity required to hold these fast-moving stars within the galaxy and prevent it from simply flying apart must be immense. Calculations revealed that Dragonfly 44 has a mass thousands of times greater than the total mass of all its visible stars, gas and dust. The only explanation is that this galaxy is swollen with dark matter, making up over 99% of its total substance. It's a galactic halo made almost entirely of this mysterious, unseen material, with a sprinkling of stars as a barely visible garnish. Finding something that emits almost no light requires a special kind of astronomical detective work. Traditional surveys that look for the glow of stars would simply pass over a dark galaxy without a second glance. The key to uncovering them lies in a combination of innovative techniques. One method involves using large telescopes to conduct deep, wide-field surveys that are exceptionally good at detecting objects with extremely low surface brightness, the faint, spread-out glow that other telescopes would miss. Once a candidate object is identified, the next step is to turn to spectroscopy. By analyzing the subtle shifts in the light from the galaxy's few stars or its trace amounts of hydrogen gas, astronomers can measure their orbital velocities. This is the crucial part. According to the laws of gravity, the speed at which stars orbit the center of a galaxy is directly tied to the total mass contained within their orbit. When the measured velocities are far too high for the amount of visible stuff present, you know you've found a dark matter-dominated system. It's like watching a handful of feathers being whipped around in a hurricane. You can't see the air creating the wind, but you know from the motion of the feathers that a powerful, invisible force is at work. The existence of these dark galaxies is far more than just a cosmic curiosity. It's a profound clue in our long-standing quest to understand dark matter itself. For decades, the leading candidate for what dark matter could be has been a class of hypothetical particles known as WIMP, weakly interacting massive particles. These particles would interact only through gravity and the weak nuclear force, making them incredibly difficult to detect directly. The prevalence of dark galaxies like Dragonfly 44 provides strong, indirect support for this cold dark matter model. It suggests that dark matter can indeed clump together under its own gravity to form the scaffolding for galaxies, and that in some cases, this scaffolding can form with very little of the normal baryonic matter, the stuff that makes up stars, planets, and us ever falling in to light it up. This tells us that dark matter is not just a passive ingredient evenly mixed throughout the cosmos, but an active architect that can build structures all on its own. The discovery of these invisible giants forces us to confront the possibility that for every brilliant spiral galaxy like our own, there could be countless dark, silent counterparts drifting through the void, a hidden population that has shaped the cosmos in ways we are only beginning to perceive. As we move from the ghostly architecture of dark galaxies, we arrive at a world that sounds like it was ripped from the pages of a science fiction epic. In a distant star system, astronomers have identified a planet that defies both our expectations of stability and composition, a carbon-rich world on a wildly unpredictable journey. This is a place where the skies would be lit not by one, but by two suns, and where the very ground beneath your feet might be composed of unimaginable riches. The planet's highly elliptical orbit sends it on a cosmic roller coaster ride, swinging breathtakingly close to its twin stars before being flung out to the icy depths of its system, a trajectory governed by a relentless gravitational tug-of-war. The drama of this planet's existence is born from its parent stars. It orbits a binary system, meaning it's caught in the gravitational field of two stars that are themselves locked in a mutual dance. This creates an environment of profound instability. Unlike the nearly circular, placid orbit of Earth around our solitary sun, this planet's path is a pronounced ellipse. Imagine a world where the seasons aren't a gentle, predictable cycle, but violent, extreme transformations. During its close approach, or periastron, the planet is blasted with intense heat and radiation from the two nearby stars, likely heating its surface to temperatures that could melt rock. Then, as it swings out to the far end of its orbit, its apastron, it enters a deep freeze, a long, dark winter where any atmosphere would likely collapse and freeze solid. This isn't a gentle oscillation. It's a constant, brutal whipsaw between inferno and icebox, a cycle that would make the planet utterly inhospitable to life as we know it. Yet, it's the planet's very composition that adds another layer of spectacular weirdness. Spectroscopic analysis suggests it is exceptionally rich in carbon. In our own solar system, planets like Earth are composed largely of oxygen and silicon, forming rocky silicates. But in a system with a high carbon-to-oxygen ratio, the chemistry of planet formation takes a dramatic turn. Under the immense pressures within such a carbon-rich world, the element could crystallize into vast fields of diamond. While it might not be a single, solid sphere of glittering gemstone, the prospect of diamond layers within its mantle, or even diamond mountains on its surface, is a very real geological possibility. This creates the mind-bending image of a world soaring through a double-sun sunset. its landscape glittering with crystalline structures on a scale we can scarcely conceive. The chaotic gravitational dynamics that create this strange path are a direct result of the three-body problem, a famous puzzle in physics that describes the complex and often unpredictable motions of three celestial bodies pulling on each other. With 2 stars and 1 planet, there is no simple, stable solution. The planet doesn't follow a smooth, Keplerian ellipse as it would around a single star. Instead, its orbit precesses, meaning the ellipse itself slowly rotates over time, making the planet's long-term path through space incredibly difficult to forecast over millennia. The gravitational kicks it receives from the ever-shifting positions of its 2 suns constantly perturb its trajectory, ensuring its journey is one of perpetual change and uncertainty. This discovery does more than just present us with a celestial curiosity. It expands our understanding of planetary diversity. It proves that planets can not only form and survive in such dynamically violent environments, but that they can also become chemically exotic, transforming common elements into extraordinary landscapes under the right conditions. This diamond world, racing between its twin suns, is a stunning testament to the fact that the universe is capable of crafting wonders far beyond the limits of our own imagination. Leaving behind the diamond world with its chaotic dance, we venture next into the realm of stellar relics, where we find a star so ancient and pristine that its very existence is a quiet but profound challenge to our cosmic history books. Designated as SDSS-J 102,915 plus 172,927, a name that belies its profound significance, this star is what astronomers call a metal-poor star. But in astronomy, metal means something very specific. It refers to any element heavier than hydrogen or helium. You see, in the fiery forge of the Big Bang, only the very lightest elements were created: hydrogen, helium, and a trace amount of lithium. Every other element in the universe, from the carbon in our bodies to the iron in our blood and the silicon in our planet, was forged later in the nuclear furnaces of stars and the violent explosions of supernova. This means that the first generation of stars, known as population 3 stars, would have been composed of nothing but that primordial hydrogen and helium. They would have been colossal, brilliant, and short-lived giants, and when they died in spectacular supernova, they seeded the cosmos with the first heavy elements, polluting the interstellar gas from which the next generations of stars would form. This is why finding a star with an extremely low metal content is like finding a perfectly preserved fossil, a time capsule from the universe's infancy. SDSS-J 102,915 plus 172,927 is such an object. Its metallicity is so incredibly low, less than 1/200,000th of the metal content of our own sun, that it should not, according to many models, even be able to form a star like the one we observe. The prevailing theory of star formation suggests that the first trace amounts of heavier elements, particularly carbon and oxygen, were crucial for cooling the primordial clouds of gas. These elements act as a kind of cosmic coolant. As the gas cloud collapses under its own gravity, it heats up, and this heat creates an outward pressure that can resist further collapse. The presence of carbon and oxygen allows the cloud to radiate away this heat, lose its pressure support, and continue collapsing into a dense star-forming core. A cloud of pure hydrogen and helium, the theory went, would have a much harder time cooling down and would therefore struggle to fragment into small, stable stars. It was thought they would only form behemoths, stars hundreds of times more massive than our Sun. Yet here is SDSS-J 102,915 plus 172,927, a star with a mass smaller than our Sun, composed of gas that is almost perfectly pristine. It somehow managed to form from a cloud that possessed virtually none of the crucial cooling agents. How did this happen? Did some other unknown cooling mechanism allow this tiny star to condense out of the primordial soup? Or does its existence imply that the very first generation of stars was more diverse than we ever imagined, that some of them were actually quite small and long-lived, and that one of those first-generation stars is somehow still shining today, hiding in plain sight within our own galactic halo? The implications are staggering. If this star is a true first-generation star, it would be a direct window into the chemical composition of the universe moments after the Big Bang, allowing us to test our fundamental models of nucleosynthesis with a living laboratory. If it is a second-generation star, its formation forces a radical rethink of the physics that governed the earliest epochs of structure formation. This single, faint point of light is a key that could unlock the mystery of how the very first lights in the cosmic dark flickered into existence, illuminating the end of the universe's dark ages and setting the stage for everything that was to come. But if an invisible galaxy challenges what we can see, then the next oddity completely redefines the concept of an object itself. Astronomers mapping the sky with state-of-the-art radio telescopes began to notice something that, at first glance, seemed like a glitch in the data: faint, perfectly circular rings of radio emission hanging in the void like celestial smoke rings. They weren't centered on any obvious galaxy or quasar, and they were absolutely enormous, each one spanning hundreds of thousands of light-years, far larger than entire galaxies. The most puzzling part, when researchers pointed optical, infrared, and X-ray telescopes at these rings, they saw nothing. These odd radio circles, or ORC, were ghosts in the radio spectrum, visible only through the eyes of radio telescopes. Their perfect symmetry and isolated nature immediately ruled out common explanations like the remnants of supernova explosions, which are far smaller and messier. The hunt for an explanation has launched a fascinating battle of theories, with each proposal more imaginative than the last. One leading idea suggests these ORCs could be the titanic shockwaves from a past, cataclysmic event in the central galaxy, now faded from view. Imagine a starburst galaxy from billions of years ago, a system where stars were being born at a ferocious rate. The combined effect of stellar winds and subsequent supernova from millions of stars could have blasted a phenomenal bubble of hot gas outward into intergalactic space. As this expanding shell of charged particles plows into the much thinner medium between galaxies, it could create a spherical shock front that acts like a giant particle accelerator, causing electrons to spiral around magnetic fields and emit the synchrotron radiation we detect as radio waves. This would make an ORC the final, fading echo of a long-concluded period of frantic star formation, a fossilized bubble from a bygone era of cosmic violence. Another compelling hypothesis points the finger at active galactic nuclei, the supermassive black holes at the hearts of galaxies. If a black hole had a past period of intense activity, spewing out colossal jets of material, the resulting energy could have inflated a pair of giant radio lobes on either side of the galaxy. What if we are seeing one of these lobes not from the side but directly end-on? From our perspective, the circular rim of the distant lobe would appear as a perfect ring, with the central galaxy too faint or too far away to be easily identified. This would be like looking down the barrel of a cosmic gun that was fired millions of years ago, seeing only the circular muzzle flash frozen in time. Yet, for all the creativity of these explanations, some of the properties of ORCs remain stubbornly difficult to fit into existing models. Their startling uniformity and the fact that they don't always have a clear central engine have prompted a more radical line of thought. Could they be the aftermath of a completely new type of event? Some have speculated very cautiously that they might be the throats of wormholes or the imprints of collisions between cosmic strings, a theoretical, one-dimensional defects in space-time left over from the universe's birth. While these ideas are far more speculative, their very consideration highlights just how perplexing these objects truly are. The discovery of ORCs isn't just about adding a new class of object to the celestial zoo. It's a powerful demonstration of how much we still have to learn about the energetic lives of galaxies and the potential for entirely new physics to manifest in the silent, invisible realms of the cosmos. They are cryptic messages written in radio waves, and we are only just beginning to learn how to read them. Moving from the silent enigmas of odd radio circles, we find a cosmic phenomenon that beats with the steady, predictable rhythm of a living heart. Far out in the depths of space, a peculiar pair of stars locked in a tight orbital embrace has been discovered, and its signal to us is unlike any other. This is the heartbeat star system, a binary where the light we receive from one of the stars doesn't just dim and brighten in the simple, predictable way of an eclipse, but rather pulses and surges in a complex, rhythmic pattern that precisely matches its orbital period. Every time the stars swing closest to one another in their elongated paths, the system flares in brightness as if taking a deep, cosmic breath before fading again as the stars pull apart. The resulting light curve, when graphed out, looks astonishingly like an electrocardiogram readout, a steady, repeating beat that signals the vibrant, dynamic life of this distant stellar partnership. The engine driving this celestial pulse is the incredible power of tidal forces, the same kind of gravitational tug that our moon exerts on Earth's oceans, but amplified to an almost unimaginable degree. In this system, the two stars aren't perfect spheres calmly circling one another at a safe distance. Their orbits are highly elliptical, meaning they spend most of their time far apart, but then periodically rush toward each other in a close, dramatic encounter. As they approach this point of closest passage, known as the periastron, the gravitational pull between them becomes immense. This force doesn't just dictate their paths, it physically stretches and squeezes the stars themselves, distorting their shapes into ovals or egg-like forms. This constant gravitational massage pumps energy into the stars, exciting powerful oscillations within their interiors. It's as if the entire star is being rung like a bell, with its gaseous layers sloshing and vibrating in resonant harmonics. These aren't small, subtle quakes. They are large-scale pulsations that actually change the star's surface area and temperature. When the star's surface expands and heats up due to these oscillations, it emits more light. When it contracts and cools, it dims. This cyclical deformation, perfectly synchronized with the orbital dance, is what creates the regular beat we observe from Earth. This discovery provides astronomers with an unprecedented natural laboratory for studying stellar interiors. Just as geologists use seismic waves from earthquakes to probe the internal structure of our planet, astrophysicists can use these tidally induced pulsations to perform a kind of stellar sonogram. By meticulously analyzing the specific frequencies and amplitudes of the brightness pulses, scientists can infer the star's density, composition, and internal processes. They can learn how energy is transported from the nuclear burning core to the surface, and how different layers of the star rotate and interact. The heartbeat star system offers a rare, clockwork-precise set of conditions that allows us to test and refine our models of stellar evolution and structure in a way that observing a single, isolated star never could. It reveals the hidden, dynamic life within what we might otherwise assume are static, placid balls of gas, showing us that stars in close relationships are constantly communicating their internal secrets through the language of light and gravity, if only we know how to listen. Now, let's turn our attention to a cosmic phantom, a wanderer in the vast emptiness between galaxies that seems to have lost its way. Imagine a cloud of pure hydrogen, gas so immense it contains enough raw material to build tens of millions of stars like our Sun. Yet, this colossal reservoir of potential isn't nestled within a galaxy. It's adrift utterly alone in the blackness of intergalactic space. This is the ghostly hydrogen cloud, a celestial enigma that appears as a faint, diffuse smudge in radio telescope data, a gigantic blob of primordial matter with no stars to light it up and no visible galactic core to call home. Its very existence forces us to ask a deceptively simple question. Where did this lonely giant come from, and what does its solitary journey tell us about the untold stories of cosmic evolution? The mystery of its origin has sparked a fascinating debate among astronomers, centered on two compelling and dramatic possibilities. The first theory paints a picture of cosmic failure on a grand scale. This cloud could be what's known as a dark galaxy that never was a vast pocket of primordial gas that, for some reason, failed to ignite. According to our models of structure formation, the gravitational pull of dark matter is supposed to draw in clouds of hydrogen gas, compressing them until the density and pressure trigger the birth of the first stars. But in this case, perhaps the dark matter halo surrounding the gas was too weak, or the cloud itself was too turbulent and never achieved the stable, cold conditions necessary for star formation to begin. It would be a fossil from the universe's early days, a stillborn galaxy that has drifted for billions of years, preserving a pristine sample of the raw material from which all galaxies are built. It's a ghost of a future that never arrived. The second, and perhaps more violent, explanation involves a spectacular galactic collision. Galaxies are not isolated islands. They exist in clusters and groups, and they sometimes interact in catastrophic ways. It's possible that this hydrogen cloud is the shredded debris from a high-speed encounter between two galaxies. As they grazed past each other, their immense gravitational forces could have acted like cosmic tidal waves, ripping vast streams of gas from their spiral arms and flinging it out into the void. This process, known as tidal stripping, can leave long, ribbon-like structures of gas stretching between galaxies. What we might be seeing is a particularly massive and isolated clump from one of these ancient ribbons, a piece of galactic wreckage that has been sailing through the intergalactic medium ever since the crash occurred. This scenario would make the cloud a stark reminder of the violent encounters that continually reshape the cosmic landscape. So, how do we even find something so ethereal and invisible? The key lies in the unique signature of neutral hydrogen gas. This fundamental element emits a faint radio wave at a very specific frequency, a wavelength of 21 centimeters. By tuning our most sensitive radio telescopes, like the Arecibo Observatory in its prime or the Carl G. Jansky Very Large Array to scan the sky for this specific signal, astronomers can effectively map the distribution of hydrogen gas even when it emits no visible light. Discovering a massive, concentrated source of this 21-centimeter emission that isn't centered on any known galaxy is the telltale sign of one of these ghostly clouds. It's like using a special filter that allows you to see only the breadth of the universe, revealing structures that are completely transparent to our optical eyes. The profound challenge this cloud presents is to our understanding of the intergalactic medium, the thin soup of gas and dust that fills the space between galaxies. We once thought of this realm as mostly empty, a near-perfect vacuum, but the discovery of these lone hydrogen clouds suggests that it might be far richer and more structured than we imagined, dotted with these invisible islands of raw material. Furthermore, the cloud's mere survival is a puzzle in itself. A cloud of gas this large, floating freely, should be under immense internal pressure. According to conventional physics, it ought to either collapse under its own gravity to form stars or, if it's too hot and diffuse, simply dissipate and mix into the surrounding intergalactic medium over a relatively short cosmic time. The fact that it has maintained its coherence for so long implies that something is holding it together. This is where the dark matter hypothesis becomes so compelling. An unseen, massive halo of dark matter could be providing the gravitational glue that keeps the cloud from flying apart, a hidden anchor for this visible ghost. If true, it would mean we are not just looking at a cloud of gas, but at the silhouette of an entire, invisible dark matter structure, a scaffolding without a building. This solitary cloud drifting in the darkness is more than just a cosmic curiosity. It is a direct probe into the most mysterious components of our universe and the violent, unseen processes that govern the birth and death of galaxies. But if ghostly clouds and runaway black holes stretch our imagination, the idea of a moon orbiting a planet in another star system takes us into a realm once thought to be the exclusive domain of science fiction. Yet, astronomers may have found exactly that, and it's a world that shatters every expectation we have about what a moon can be. Designated as Kepler 1625b, this candidate is not a small, rocky body like our own moon. The data suggests something almost unbelievable, a possible exomoon roughly the size of the planet Neptune. Imagine a gas giant, a behemoth many times larger than Jupiter, and then picture a moon in its sky that isn't a pinprick of light, but a colossal, swirling marble of vibrant blue, a world in its own right with a thick, enveloping atmosphere. This isn't just a moon, it's a double planet system on a scale that dwarfs anything in our own cosmic neighborhood. The evidence for this extraordinary object comes from the meticulous, painstaking work of analyzing data from the Kepler Space Telescope. Kepler hunted for planets using the transit method, watching for the telltale, periodic dimming of a star's light that occurs when an orbiting planet passes in front of it. In the case of the star Kepler 1625, astronomers noticed a pattern that was deeply unusual. The data showed the primary dip in brightness from a giant planet, but then, both before and after this main transit, there were additional, smaller dips in the star's light. This secondary signal is the key. It suggests that something large is trailing the planet and then leading it, casting its own shadow as it goes. After rigorously ruling out other potential causes, such as stellar activity or the presence of a second planet in the system, the most plausible explanation remaining is a massive moon on a wide orbit. The inferred size of this object, based on the depth of its dimming effect, points to a diameter several times that of Earth, placing it firmly in the Neptune-sized category. The implications of such a discovery are revolutionary, starting with the very way moons are born. In our solar system, we have three primary models for moon formation. Large moons like Earth's are thought to have formed from a giant impact where a Mars-sized body crashed into the young Earth, ejecting debris that coalesced into our moon. Many of the moons orbiting Jupiter and Saturn are thought to be captured asteroids or Kuiper belt objects, gravitationally snatched into orbit during the solar system's chaotic early days. A third method involves moons forming from the same swirling disk of gas and dust that created their parent planet, a miniature version of how planets form around a star. But a Neptune-sized moon doesn't fit neatly into any of these boxes. It is far too massive to be the product of a giant impact without utterly destroying the parent planet. Its large size also makes capture incredibly difficult. The complex gravitational dance required to slow down such a massive object and have it settle into a stable orbit is statistically very unlikely. This leaves the circumplanetary disk model as the most probable origin story, suggesting that the disk of material around this giant exoplanet was unimaginably massive and rich, allowing a true subplanet to coalesce within it. This would mean that moon formation can, under the right conditions, operate on a staggering planetary scale, creating systems within systems that are far more grand and complex than we ever anticipated. The potential for this moon to possess its own thick atmosphere adds another layer of breathtaking possibility. A world of this size would have the gravitational strength to hold onto a substantial gaseous envelope, potentially composed of hydrogen and helium, much like the ice giants in our own solar system. But the most tantalizing prospect lies in the concept of habitability. We often focus on the habitable zone of a star, the region where temperatures are just right for liquid water to exist on a planet's surface. But here we are forced to consider the concept of a moon's habitable zone. Even though this particular exomoon candidate orbits a gas giant that is likely far too close to its star to be in the traditional habitable zone, the discovery proves that such large, complex moons can exist. It opens the door to imagining a different kind of habitable world, a Neptune-sized moon with a rocky core orbiting a gas giant that is comfortably within its star's Goldilocks zone. Such a moon could potentially have a temperate climate, liquid water on its surface or within its layers, and a protective atmosphere, all under the majestic view of a giant planet filling its sky. The existence of Kepler 1625b, even as a candidate, fundamentally expands the real estate of the cosmos where life could potentially take hold, moving the goalposts from just planets to include their potentially vast and diverse families of moons. Of course, the strange, silent traveler from the depths of interstellar space deserves a chapter all its own. In 2017, our solar system received its first confirmed tourist from another star. It was a moment of profound significance, the astronomical equivalent of finding a message in a bottle washed up on a distant shore. The object was named Oumuamua, a Hawaiian word that beautifully means a messenger from afar arriving first. And what a strange messenger it was. From the moment it was spotted racing away from the sun, it was clear this was no ordinary comet or asteroid. Its path was the first clue to its otherworldly origin, a hyperbolic trajectory that meant it was not bound by the sun's gravity and was merely passing through on its way back out to the galaxy. But the real mystery, the one that would ignite fierce debate and capture the world's imagination, was not just where it came from, but what it was made of and why it was behaving so oddly. The initial observations painted a perplexing portrait. As telescopes scrambled to track it, they determined that Oumuamua was tumbling chaotically through space like a poorly thrown football. It was also exceptionally elongated, with estimates suggesting a shape like a pancake or a cigar, perhaps 10 times longer than it was wide. This alone was unusual, as most solar system objects are more lumpy or spherical. But the most baffling piece of the puzzle came when astronomers precisely calculated its orbit. They found that it was experiencing a tiny but consistent additional acceleration, a slight boost in speed that could not be explained by the gravitational pull of the sun or any of the planets. It was as if an invisible hand was giving it a gentle, continuous push. For a natural object, this usually points to one clear culprit: outgassing. When a comet approaches the sun, its icy surface heats up, turning frozen gases directly into vapor in a process called sublimation. This jetting gas acts like a natural rocket engine, providing the non-gravitational push that can alter a comet's path. The problem with Oumuamua was that it showed absolutely no visible signs of this activity. When a comet outgasses, it typically develops a bright, fuzzy coma, a cloud of gas and dust, and often a tail, as the solar wind blows the material away. Oumuamua, however, was completely barren. No coma, no tail, no dusty envelope of any kind. Our most sensitive instruments detected nothing being released from its surface. So, if it was outgassing, it was doing so in a way we had never seen before, with a gas that was invisible to our telescopes and without releasing any of the dust that normally accompanies such eruptions. This paradox led scientists to propose some ingenious natural explanations. One compelling hypothesis suggests that Oumuamua could be a cosmic iceberg, composed largely of molecular hydrogen ice. Hydrogen is the most common element in the universe, but it's incredibly difficult to freeze, requiring temperatures only found in the densest, coldest cores of giant molecular clouds. If such an object were to form, it would be a stealthy traveler. As it passed close to our sun, the heat would cause the solid hydrogen to sublimate, creating the necessary jet-like thrust. Crucially, hydrogen gas is invisible in the wavelengths we use to detect comet comas, and its sublimation would not kick up any dust, perfectly explaining the lack of a visible tail. This would make Oumuamua a pristine relic from the birth of a distant star system, a fragile chunk of a protoplanetary disk that was ejected into the galactic void. Another fascinating natural theory posits that Oumuamua is not a single solid object at all, but a dust bunny on a cosmic scale, a loose, fractal-like aggregate of dust and ice, what some scientists call a dust iceberg. The idea is that in the outer reaches of its home system, fine dust particles could have clumped together into a very porous, low-density structure, held together by weak electrostatic forces rather than solid ice. As this fluffy object was heated by the sun, not only would ices sublimate from within its labyrinthine interior, but the entire structure might have been puffing away, releasing dust grains too small for us to detect from Earth. The combined effect of this gentle, widespread mass loss could have provided the observed acceleration without the concentrated jets that create a traditional cometary coma. In this scenario, Oumuamua might not even exist anymore, having slowly disintegrated into a cloud of fine dust after its close encounter with our star. Yet, the very strangeness of these required explanations, the need to invoke exotic ices or incredibly fragile structures, is what opened the door to a more speculative and decidedly more thrilling possibility. Could Oumuamua's behavior be evidence of an artificial origin? The most famous proponent of this idea is Harvard astronomer Avi Loeb, who suggested we must at least consider the possibility that Oumuamua was a piece of advanced alien technology, perhaps a light sail, a vast, thin sheet designed to be pushed by the radiation pressure from starlight. A light sail made of a material just a fraction of a millimeter thick could have the exact pancake-like shape inferred for Oumuamua. Its unusual acceleration could be explained by the gentle, continuous pressure of sunlight on its vast surface, requiring no outgassing whatsoever. The object's tumbling motion could then be explained as a derelict craft, no longer under active control, drifting aimlessly through the galaxy. While the scientific community largely favors a natural origin, acknowledging that the universe is often stranger than fiction, this hypothesis forced a crucial conversation about how we approach the unknown. It reminded us that when we encounter something truly anomalous, we must be open to all possibilities, no matter how unconventional, and that the pursuit of knowledge requires both rigorous skepticism and the courage to ask big, bold questions. Oumuamua's true nature may forever remain a mystery, a secret it carried in from the dark and took with it as it faded from view, but its legacy is indelible. It was our first tangible proof that we live in a galaxy teeming with unseen wanderers, and it challenged us to be better, more creative detectives in the ongoing investigation of the cosmos. Leaving behind the silent, tumbling mystery of Oumuamua, we arrive at an object that is the complete opposite, a cosmic beacon screaming its presence as it tears through the void. Astronomers have discovered a pulsar that has earned the nickname the Cosmic Cannonball, and it's a title well-deserved. This particular stellar remnant is hurtling through space at a blistering speed of nearly 2.5 million miles per hour, a velocity so immense it could journey from Earth to the Moon in just about 10 minutes. But this isn't a silent traveler. As it flees the scene of its own violent birth, it leaves behind an incredible contrail, a brilliantly glowing wake of high-energy particles and shocked gas stretching for dozens of light years, a stark testament to its incredible journey. To understand how this cannonball was fired, we need to rewind to its dramatic origin story, a supernova explosion. Pulsars themselves are the rapidly spinning, incredibly dense cores of massive stars that have died in these cataclysmic events. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses under its own immense gravity in a matter of seconds. The outer layers of the star then rebound off this newly formed, ultra-dense core and are blasted out into space in a titanic explosion visible across galactic distances. However, this explosion is rarely perfectly symmetrical. It's thought that a slight imbalance in the detonation, a kind of cosmic lopsidedness, can act like a rocket engine, giving the newborn neutron star at the center a powerful kick. Imagine a balloon being released and spinning wildly as the air rushes out. the supernova's uneven blast provides a similar but unimaginably more powerful thrust. This kick is what launches the pulsar on its high-speed escape from the stellar wreckage, turning it into a runaway stellar corpse. The sheer velocity of the cannonball pulsar is more than just a record-breaking curiosity. It's a crucial clue that helps astronomers piece together the chaotic physics of a star's final moments. The force required to accelerate an object with the mass of our entire sun, packed into a sphere the size of a city to such an incredible speed, is almost beyond comprehension. By studying the speed and trajectory of pulsars like this one, scientists can work backwards to model the mechanics of the supernova kick itself. The direction the pulsar is moving can even point back to its place of birth, often to a specific supernova remnant, allowing us to connect the dot between the ancient explosion and the object it created and ejected. This cannonball isn't just running away, it's telling us a story about the most violent and transformative process in the life cycle of stars, and what of that spectacular trail it leaves behind. This isn't a simple vapor trail like a jet might paint across our sky. The pulsar, a magnetized powerhouse, is spinning rapidly and beaming out intense winds of charged particles. As this pulsar wind slams into the tenuous gas that drifts between the stars, the interstellar medium, it creates a bow shock, much like the wave that forms at the front of a speedboat. The interaction between these high-energy particles and the surrounding gas causes it to glow, particularly in X-ray wavelengths, painting a long, sleek arrow in the cosmos that points directly back to the pulsar's path. This glowing wake does more than just mark the pulsar's route. It acts as a probe, allowing scientists to measure the density and composition of the interstellar material it is passing through. We are essentially using this cosmic cannonball as a tool to illuminate the invisible fabric of our galaxy, revealing the subtle structures of the space between the stars through the brilliant, energetic signature of its passage. We've traced the paths of runaway black holes and navigated the silent currents of dark galaxies, but now we turn our attention to a ghost that permeates the entire cosmos, a chill in the very afterglow of creation. To understand it, we first have to journey back almost all the way to the beginning, when the universe was a seething, opaque soup of particles and energy, too hot for atoms to even form. Light was trapped, constantly scattering off free electrons. Then, about 380,000 years after the Big Bang, everything cooled just enough for electrons and protons to combine into neutral hydrogen atoms. In that moment, which astronomers call recombination, the universe suddenly became transparent, and that primordial light, freed from its prison, began streaming across the cosmos. That light is still all around us today, stretched and cooled by the relentless expansion of the universe into a faint microwave hum that bathes the entire sky. This is the cosmic microwave background, or CMB, and it is the oldest fossil we can possibly observe, a baby picture of the universe itself. When scientists create exquisitely detailed maps of this background radiation, they expect to see a nearly uniform tapestry with only tiny, random fluctuations in temperature, the seeds that would one day grow into galaxies and clusters. For the most part, that's exactly what they found, confirming our core theories about the Big Bang. But then they noticed something odd, something that refused to fit the pattern. In the southern celestial hemisphere, there is a vast, sprawling region that is significantly colder than the surrounding average. This is the Great Cold Spot, an anomaly so large it spans nearly 2 billion light-years, a staggering void of cold in the universe's first light. Its temperature is only a few hundred millionths of a degree lower than its surroundings, but in the hyper-precise world of cosmology, that deviation is massive and deeply significant. It's a feature on a scale that our standard models of cosmic evolution simply don't predict, a bruise on the face of the early universe that demands an explanation. Cosmologists have put forward two primary and radically different hypotheses to account for this mysterious chill. The first is a profoundly cosmic one. the Great Cold Spot could be the shadow of a collision with a parallel universe. This idea springs from the theory of eternal inflation, which suggests our universe is just one bubble in a vast, ever-expanding multiverse. In this model, other bubble universes could, in principle, collide with our own. If such a collision occurred in the universe's infancy, the immense energy released could have left an imprint on the fabric of space-time, a kind of scar that would manifest as a large, cold region in the CMB. It's a breathtaking concept that we might be seeing the tangible evidence of a neighboring cosmos brushing against our own in the first moments of time, a fossilized kiss from another reality. The second and more conservative explanation brings the cause closer to home within our own universe, but posits a structure of almost unbelievable emptiness. This theory suggests the cold spot is not a primordial imprint at all, but a secondary effect caused by a phenomenon known as the integrated Sachs-Wolfe effect. As light from the CMB travels across the universe toward us, it passes through regions of varying gravitational pull. When it climbs out of a deep gravitational well, like that of a massive galaxy cluster, it loses a tiny amount of energy, shifting it slightly to the red or colder part of the spectrum. Normally, these effects are small and cancel out across the sky. However, if the light passed through an exceptionally large and underdense region of space, a cosmic void containing far fewer galaxies than average, on its way to us, the cumulative energy loss could be significant. In this scenario, the Great Cold Spot would be the shadow of a supervoid, a staggering emptiness in the cosmic web so vast that its gravitational influence imprints a cold patch on the CMB. The challenge has been to find such a void. Some surveys have indeed identified a large underdense region in the general direction of the cold spot, but its size and emptiness don't quite seem sufficient to explain the entire temperature anomaly, leaving the mystery tantalizingly unresolved. This ongoing debate is more than just academic. It strikes at the heart of how we understand the universe's structure and its most fundamental laws. If the cold spot is indeed evidence of a multiverse, it would be one of the most profound discoveries in the history of science, fundamentally altering our cosmic address and our understanding of reality itself. If instead it is caused by a supervoid, it forces us to revise our models of how the large-scale structure of the universe forms, suggesting the existence of emptier and larger voids than we thought possible. The Great Cold Spot remains one of the most significant and persistent anomalies in modern cosmology, a quiet, cold question mark written into the oldest light there is, reminding us that even our most successful theories are still incomplete, and that the universe's first whisper still holds secrets we are only just learning to hear. Just when we think we've seen every possible configuration of a solar system, the cosmos unveils a world that seems to defy all our expectations of celestial order. Imagine standing on the surface of a planet where the sky is not dominated by one sun, but by three. This is the reality of a planet discovered in the HD 188753 system, a world locked in a breathtaking gravitational ballet with a trio of stars. In this system, the planet orbits the primary star, a star that is itself locked in a tight binary partnership with another star, while a third, more distant star circles this central pair in a much wider orbit. The result is not a simple, stable loop, but an incredibly complex and rhythmic orbital dance, a cosmic waltz choreographed by gravity on the grandest of scales. The daily experience on such a world would be something straight out of a dreamscape, with light and shadow playing in ways we can barely conceive. For long stretches of time, the planet's inhabitants, if any could survive the conditions, would experience relatively normal days, with one bright sun moving across the sky, while the two other suns appear as intensely brilliant stars, often close enough together to be a permanent, dazzling double star in the heavens. But then, as the planet and stars move through their orbits, there would be periods where all three suns rise and set together, casting triple shadows that create a landscape of profound and shifting contrast. The day of longest daylight might be a time when one sun sets only for the second to rise, followed by the third, creating a twilight that lasts for hours or even days depending on the orbital periods. There could be seasons defined not by axial tilt, but by the changing alignments of the stars themselves, with some eras bringing perpetual daylight for half the planet's year, and others offering a cycle of sunrises and sunsets so complex they would be nearly impossible to predict without an advanced computer. The very definition of a day would become fluid, a concept tied more to the intricate clockwork of the triple star dance than to the simple rotation of the planet itself. For such a world to exist at all is a testament to a very precise and delicate gravitational balance. The sheer notion of a stable orbit in a multi-star system was long considered a major puzzle in astrophysics, as the gravitational pulls from multiple massive bodies can easily become chaotic, either flinging a planet out into interstellar space or sending it crashing into one of its suns. The key to stability in a triple system like this lies in the hierarchy of the orbits. In a hierarchical triple system, the stars themselves are arranged in a stable configuration. The two closest stars orbit each other very tightly, forming a binary pair that acts from a distance, almost like a single gravitational point. The planet then orbits this central binary pair at a safe distance, far enough away that the tugs from the individual stars largely average out. Meanwhile, the third, outermost star orbits this whole central system, the binary pair and its planet, on a much wider, slower path. This creates a kind of gravitational buffer. The planet feels a stable, dominant pull from the central binary, while the distant third star provides only a gentle, long-period perturbation that slightly stretches and contracts the planet's orbit over millennia rather than breaking it completely. It's a celestial arrangement that is stable only within a very specific range of distances and mass ratios, a fragile niche in the orbital parameter space that this planet somehow found and has maintained for billions of years. The discovery of planets in systems like this profoundly expands our understanding of where worlds can form and persist. It demonstrates that planet formation is a robust process, capable of occurring even within the dynamic and potentially disruptive environment of a multiple star system. This forces astronomers to reconsider the classic concept of a habitable zone. In a single star system, the habitable zone is a relatively straightforward shell around the star where temperatures are right for liquid water. But in a triple system, the energy input is wildly variable. The planet receives light and heat from 3 different sources, and the combined flux changes dramatically depending on their positions. A planet might oscillate in and out of a traditional habitable zone as the stars move, creating cycles of extreme heating and cooling. This doesn't necessarily rule out life, but it suggests that any life that did arise would have to be incredibly resilient, capable of hibernating through long, frozen winters or withstanding intense periods of radiation. The existence of this triple sun world challenges us to think of habitability not as a static place, but as a dynamic state, one that could potentially be maintained even in some of the most gravitationally complex neighborhoods in the galaxy. Just as we grapple with the ghosts of cosmic structures and the cold spots in the background radiation, we stumble upon a different kind of cosmic vanishing act, a stellar death that appears to have happened without a star. Astronomers witnessed a brilliant supernova explosion, catalogued as SN 2016 GKS, and immediately began the standard detective work of tracing it back to its origins. They combed through archival images of that precise patch of sky, taken by the Hubble Space Telescope and other powerful observatories over the preceding years, fully expecting to find the progenitor star, the massive, unstable giant that had just met its violent end. But when they looked, they found nothing. The patch of sky where the supernova erupted was, for all intents and purposes, empty. There was no sign of a star massive enough to have exploded in such a fashion. This was not just a missing person case, it was a cosmic murder mystery where the victim had seemingly never existed. The implications of this empty supernova strike at the very heart of our understanding of how massive stars live and die. Our established models of stellar evolution are quite clear. Only stars with a core mass at least 8 times greater than our Sun possess the gravitational might to end their lives in a core collapse supernova. In the final million years or so of their lives, these stars become luminous supergiants, swelling to enormous sizes and burning with a ferocious intensity that makes them easily detectable in nearby galaxies. When such a star explodes, we should be able to look back at pre-explosion images and point directly to the star that is no longer there. The absence of a progenitor is therefore not a minor puzzle, it's a fundamental challenge. It suggests either that our estimates for the minimum mass required for a core collapse supernova are wrong, or that some stars can somehow hide their true nature in the years leading up to their cataclysmic demise. Scientists have proposed several compelling scenarios to explain this ghostly explosion. One leading theory suggests the progenitor star was not a solitary red supergiant, but was instead shrouded in a thick, dense cocoon of dust and gas. In the final millennia before its death, a massive star can undergo violent convulsions, ejecting vast amounts of its own outer layers into the surrounding space. If this material is ejected in a series of eruptions that form a nearly opaque shell around the star, it could effectively render the star invisible at the wavelengths our telescopes use to search for it. The star would be there, burning brightly, but its light would be absorbed by the surrounding dust and re-radiated as invisible infrared light. When the star finally did explode, the supernova's initial shockwave would have blasted through this cocoon, suddenly revealing the cataclysm within. In this case, we didn't see the star not because it wasn't there, but because it was wearing a cosmic disguise, a veil it only cast off in its final destructive moment. Another, more radical possibility is that the star was what's known as a failed supernova. This theory hinges on the idea that some stars at the lower end of the mass range for core collapse might not produce a traditional, luminous explosion at all. Instead of rebounding in a brilliant supernova, the core could collapse directly into a black hole, with the star's outer layers falling inward, never to be seen again. The entire star would simply and quietly vanish from the sky. However, SN 2016 GKS was a bright supernova, which seems to contradict this direct collapse model. To bridge this gap, astronomers have theorized about an intermediate scenario, a stellar core that collapses into a black hole, but where the infall of the outer layers is somehow halted or reversed for a brief period, perhaps by the intense neutrino flux or a last-minute energy release, resulting in a weaker, ultra-stripped supernova. This explosion would be significantly fainter than a typical supernova, and its progenitor star, having shed most of its envelope long before, would have been correspondingly much dimmer and harder to detect in pre-explosion images. The investigation into these empty supernovae forces us to refine our astronomical search techniques. The absence of evidence in optical wavelengths has made scientists turn to other parts of the electromagnetic spectrum. If a progenitor is shrouded in dust, it should glow brightly in the infrared. This has spurred a new wave of analysis, with astronomers meticulously scouring infrared data from telescopes like Spitzer and James Webb for hidden, dusty giants that might be future supernova candidates. Every time we find one of these empty explosions, it's a humbling reminder that our view of the cosmos is limited by the windows through which we look. A star that is invisible in optical light may be blazingly obvious in infrared, and a faint, stripped star may simply have been too dim for our telescopes to notice before its final act. Each of these mysterious explosions is not a failure of our models, but a clue, pushing us to develop more sensitive instruments and more nuanced theories about the diverse and often hidden ways that stars conclude their epic life cycles. Now, from the shadowy realms of missing stars and ghostly supernova, we turn our attention to a cosmic entity that is anything but shy, a true titan of magnetic force known as a magnetar. Imagine, if you will, a star so dense that a single teaspoon of its material would weigh billions of tons on Earth, a neutron star. Now, take that already extreme object and imbue it with a magnetic field of almost incomprehensible power, one that is quadrillions of times stronger than the Earth's protective magnetic shield and millions of times more intense than the Sun's. This is not just a star, it is a magnetic monster, a celestial powerhouse whose very presence warps the fabric of reality around it in the most dramatic ways. The sheer strength of a magnetar's magnetic field defies easy analogy. If you could bring one to within a few 100,000 miles of Earth, a dangerously close approach, the consequences would be apocalyptic. The intense magnetic field would not just scramble every compass and electronic device on the planet. It would literally pull the iron right out of your blood from that immense distance. It exerts a force so powerful that it can actually distort the atomic structure of matter itself, creating a strange, crystalline crust on the star's surface that is stronger than steel. The environment surrounding a magnetar is a perpetual storm of trapped particles and radiation, a seething maelstrom where physics is pushed to its absolute limits. This unimaginable magnetic energy doesn't just sit idly by. It makes its presence known in the most violent outbursts in the universe since the Big Bang. Magnetars are the suspected engines behind rare, colossal flashes of energy known as soft gamma repeaters and giant flares. In a fraction of a second during one of these eruptions, a magnetar can release more energy than our Sun will emit over its entire 10 billion-year lifespan. This cataclysm is born from a phenomenon called a starquake. The magnetar's incredibly rigid, crystalline crust is under immense strain from the twisting and shearing of the magnetic field lines anchored within it. Like a tectonic plate on Earth, this crust can suddenly crack and slip. But when a magnetar's crust fractures, the event is of a different magnitude entirely. The release of stress unleashes a catastrophic rearrangement of the magnetic field, which in turn accelerates particles to nearly the speed of light, resulting in a flash of gamma rays and X-rays so brilliant it can temporarily outshine every other source in the galaxy combined, even from tens of thousands of light years away. The existence of such magnetic monsters poses a significant challenge to theories of stellar evolution. The leading explanation for their creation, known as the dynamo theory, suggests they are born in the furious chaos of a supernova. When a very massive star collapses, its core spins up to incredible speeds, much like a figure skater pulling in their arms. If this newborn neutron star is spinning hundreds of times per second, its turbulent, convecting interior of superfluid neutrons and protons could act like a gigantic electrical generator, amplifying a pre-existing magnetic field to these ludicrous strengths in a matter of seconds or minutes. However, this theory has its limits. It seems to require a very specific set of initial conditions, a very rapid rotation and a particular mass, to produce a magnetar rather than a more ordinary neutron star or pulsar. The fact that magnetars appear to be relatively rare suggests that the pathway to creating one is a precarious cosmic tightrope walk, and their discovery forces astronomers to refine their models of exactly what happens in the first few moments after a star's core collapses. Observing these objects is a monumental task in itself, precisely because their most interesting behavior, the giant flares and starquakes, is unpredictable. Scientists cannot simply point a telescope at a known magnetar and wait for it to erupt. They must engage in long-term monitoring campaigns, hoping to catch one in the act. And when a flare does happen, it's so intensely bright that it can saturate the detectors on our most sensitive space observatories like Swift and Fermi, effectively blinding them for a brief moment. To study the aftermath, astronomers use a technique called X-ray timing, carefully measuring the tiny, regular pulses of X-rays that rotate with the star. By analyzing how these pulses change in frequency and intensity following a starquake, they can probe the internal structure of the magnetar and the dynamics of its super-dense matter, learning about the physics of a state of existence that can never be recreated in any laboratory on Earth. The study of these magnetic leviathans is more than just cataloging cosmic extremes. It is a direct investigation into the behavior of matter under the most intense conditions the universe has to offer, pushing our understanding of fundamental physics to the very brink. But just when we think we have a handle on these magnetic monsters, the universe reveals a new layer of their volatility. Astronomers have observed magnetars undergoing what can only be described as a cosmic seizure, a sudden, violent, and unpredictable change in their rotation known as a glitch. Imagine a hyper-precise cosmic clock spinning with unwavering regularity for years, and then, in an instant, it stutters, its rhythm abruptly jumping to a faster pace. This is precisely what was witnessed with a magnetar officially catalogued as SGR 1935+2154. For a long time, this distant object pulsed with a steady, predictable beat. Then, without any warning, its spin rate suddenly increased by a tiny but significant fraction. This event, a magnetar glitch, is a window into the incredible stresses and strains at work deep within one of the most extreme objects in existence. The leading explanation for this bizarre behavior points to a phenomenon occurring beneath the star's solid crust in its mysterious quantum interior. A magnetar is not a uniform ball of matter. It's thought to have a complex layered structure. Beneath the rigid, crystalline crust of iron nuclei lies a bizarre quantum soup known as a neutron superfluid. This superfluid is a state of matter where neutrons pair up and flow with absolutely zero friction or viscosity. Under normal conditions, this superfluid is effectively locked to the rotation of the star's solid crust, spinning along with it. However, as the magnetar ages and its powerful magnetic field applies a braking force, the solid crust gradually slows down. The frictionless superfluid inside, however, resists this slowdown. It wants to keep spinning at its original, faster rate. This creates a rotational lag, a growing differential between the speed of the outer crust and the inner superfluid. It's like spinning a raw egg and then stopping it. The liquid yolk inside will keep swirling for a moment after the shell has stopped. In the case of a magnetar, this isn't a momentary effect but a build-up of immense pent-up rotational energy. So, what triggers the sudden release? The culprit is likely a starquake, a catastrophic fracture in the magnetar's incredibly strong crust. This crust is under continuous and unimaginable stress, not just from the star's rotation, but from the titanic power of its own magnetic field, which is constantly twisting and straining the solid surface. When the strain becomes too great, the crust suddenly cracks and shifts, much like tectonic plates on Earth during an earthquake, but with energy levels that are almost beyond comparison. This seismic event has two immediate consequences. First, the starquake itself can cause a tiny change in the star's shape, making it slightly more spherical. Just as a figure skater pulls their arms in to spin faster, this sudden contraction causes the entire star's crust to spin up in a fraction of a second, the glitch we observe. Second, and more importantly, the starquake may suddenly unlock the superfluid. The fracture could disrupt the microscopic vortices that usually pin the superfluid to the crust, allowing vast reservoirs of the fast-spinning inner liquid to transfer their momentum outward in a tremendous surge, violently kicking the crust to a faster speed. Studying these glitches provides an unprecedented opportunity to probe the internal structure of a neutron star, something no laboratory experiment could ever hope to recreate. By meticulously analyzing the exact timing and magnitude of the spin-up, astrophysicists can perform a kind of celestial ultrasound. The way the star recovers from the glitch, whether it settles back to its original speed quickly or slowly, or exhibits tiny oscillations, reveals critical information about the viscosity of the superfluid, the rigidity of the crust, and the complex interaction between them. It's a direct measurement of the physics governing matter at several times the density of an atomic nucleus. Each glitch is a violent telegram from the heart of a stellar corpse, delivering data on the fundamental forces that govern the most extreme states of matter in the universe. If dark galaxies are the hidden scaffolding of the cosmos, then the discovery of a galaxy that seems to have none of that scaffolding at all is a paradox that cuts to the very core of our theories. This brings us to NGC 1052 DF2, a galaxy that became an instant celebrity for what it apparently lacks. DF2 is what's known as an ultra-diffuse galaxy. It's large, about the size of our Milky Way, but it contains only about 1/200th the number of stars, making it incredibly faint and ghostly. When astronomers first studied it, they expected to find the same story told by Dragonfly 44, a huge mass of dark matter holding its sparse stars together. They measured the velocities of 10 globular clusters, those bright, dense groups of stars orbiting the galaxy's center. To their complete astonishment, they found these clusters were moving remarkably slowly. The velocity measurements were so low that they indicated the total mass of the galaxy was almost exactly equal to the mass of its visible stars, gas, and dust. There was simply no room left for dark matter. This was like watching a handful of feathers drifting gently on a calm breeze with no hurricane in sight to explain their motion. The finding was so counterintuitive that it sent shockwaves through the astrophysics community. The implications of this discovery are profound and deeply challenging. For decades, the prevailing model of cosmology, known as the lambda cold dark matter model, has posited that dark matter is not just an ingredient in galaxies, it is the fundamental framework upon which all galaxies are built. According to this model, the gravitational pull of dark matter halos is what first draws in the normal baryonic matter, the gas that eventually forms stars. Dark matter is the cosmic architect, and the luminous galaxy we see is just the decorative finishing touches. A galaxy with no dark matter directly undermines this foundational idea. It suggests that galaxies can form and persist through some other, entirely different process. If one galaxy can exist without dark matter, then dark matter cannot be absolutely necessary for galaxy formation, forcing us to reconsider the very sequence of events that gave rise to the structures we see in the night sky. Naturally, a discovery this radical was met with intense scrutiny and a healthy dose of skepticism. The primary debate has centered on the distance to DF2. Measuring the velocity of the globular clusters tells you the mass inside their orbits, but to convert that velocity into an actual mass value, you need to know the galaxy's precise distance from us. A group of researchers using the Hubble Space Telescope initially placed DF2 at about 65 million light-years away. This distance was crucial because it set the scale for the size of the orbits of the globular clusters. At that distance, their slow speeds pointed to a very low mass. However, another team later used a different, highly precise method involving the tip of the red giant branch, a kind of standard candle where the brightness of the oldest, brightest red giant stars is used to gauge distance, and proposed the galaxy was actually much closer, only about 42 million light-years away. If this closer distance is correct, the galaxy would be physically smaller. The globular clusters would be on tighter orbits, and their same measured velocities would actually imply a much higher mass, one that could include a significant amount of dark matter after all. This ongoing debate highlights the incredible difficulty of doing extragalactic astronomy, where a seemingly minor correction in distance can completely overturn a revolutionary conclusion. Beyond the technical debate over measurements, the existence of a dark matter-free galaxy, if confirmed, offers a powerful piece of evidence in a different cosmic argument. For years, a small but persistent group of scientists has advocated for modified Newtonian dynamics, or MUND. This theory proposes that there is no dark matter at all, and that instead our understanding of gravity itself is incomplete. MUND suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies, which would explain the high rotation speeds we observe without invoking invisible matter. However, man has struggled to explain all galactic phenomena, particularly the behavior of galaxy clusters. The discovery of DF2 is actually a huge problem for men. If gravity is modified, then every galaxy should show the same effects in its low acceleration regime. But in DF2, the stars are moving exactly as Newtonian gravity predicts they should for the amount of visible mass present. In other words, DF2 behaves precisely as man would not predict, while being a potential headache for the standard dark matter model. Ironically, a galaxy with no dark matter ends up being one of the strongest arguments for the existence of dark matter as a real, physical substance, because it shows that the dark matter can be decoupled from the visible matter. It proves that dark matter is not an immutable property of gravity, but a separate component that can be present or absent, like a removable scaffold. So, how could a galaxy possibly end up without its dark matter? The most compelling theory is one of violent cosmic theft. Imagine a large, primordial galaxy with its full complement of dark matter. Billions of years ago, it could have had a very close encounter with an even more massive galaxy. As it swung by, the immense tidal gravitational forces from the larger galaxy could have acted like a cosmic cheese grater, stripping away the diffuse, loosely bound dark matter halo entirely, while the more concentrated, dense clumps of stars and gas within the smaller galaxy managed to hold together and survive the ordeal. This would leave behind a ghostly stellar system, a galaxy of stars that has been forcibly separated from its dark matter anchor. This scenario provides a natural, if dramatic, explanation and fits well with our understanding of how galactic interactions can tear systems apart. The hunt is now on for more such galaxies to see if they are all found near massive neighbors that could have robbed them, or if they exist in isolation, which would present an even deeper puzzle. Whether a measurement anomaly or a genuine cosmic rebel, NGC 1052DF2 has irrevocably sharpened the debate, proving that the universe still holds surprises that can force us to question our most deeply held beliefs about how the cosmos is built. Journeying from the heart of a lone galaxy stripped of its dark matter, we arrive at a world that feels instantly familiar from science fiction, yet is stranger than any screenwriter could have conceived. Imagine a sky dominated not by one, but by two suns, their light casting ever-changing double shadows across a landscape that might be more familiar to Luke Skywalker than to any Earth-bound astronomer. This is the reality of a Tatooine planet, a world locked in a gravitational dance with a binary star system. But the latest discovery in this exotic category adds a breathtaking new layer of complexity. This particular planet isn't just a dry, desert world. It is enveloped by a colossal, swirling disk of dust and debris, a vast cosmic construction zone that transforms the entire system into a dynamic and turbulent environment. The presence of this circumplanetary disk is a game-changer for our understanding of such exotic worlds. We've long known that planets can form from disks of gas and dust around young stars, and that moons often form in smaller disks around newborn planets, much like the disk that is thought to have given birth to our own moon. But finding a massive, dusty disk around a planet in a fully matured binary star system is a different matter entirely. This isn't a fleeting feature from the system's infancy. It's a persistent structure, a thick shroud of fine rock and ice particles that continuously interacts with the intense and variable radiation from its two parent stars. The planet itself likely experiences conditions far more extreme than those on any world in our solar system. The gravitational pull from two stars creates a complex and ever-shifting environment, with tidal forces that constantly flex the planet's interior, potentially driving intense volcanic activity and reshaping its surface over eons. The influence of this dusty disk on the planet's potential climate is profound and multifaceted. Think of the disk as a gigantic, orbital sunshade and thermostat, but one with a mind of its own. On one hand, the dense inner regions of the disk could act as a physical barrier, scattering and absorbing a significant portion of the stellar radiation before it ever reaches the planet's atmosphere. This could create a powerful cooling effect, potentially preventing the world from becoming a scorched hellscape despite its proximity to two heat sources. Conversely, the disk itself is not inert. The countless dust particles absorb stellar energy and re-radiate it as infrared heat, effectively creating a warm, glowing cocoon around the entire planetary system. This could lead to a surprisingly temperate environment on the planet's surface, a gentle warmth maintained by the encircling ring of dust rather than by direct sunlight. The climate would not be dictated by a simple day-night cycle, but by the complex interplay of the two stars' light and the shifting opacity and temperature of its own personal debris field. The planet might experience seasons governed not by axial tilt, but by its position relative to the disk and the stars, leading to eras of global dust storms or crystalline clarity. This chaotic environment, however, is also a spectacular nursery for new worlds. The circumplanetary disk is the very stuff from which moons are born. Within this swirling maelstrom of dust and rock, particles collide and stick together, slowly building up larger and larger bodies through a process called accretion. The presence of two stars adds a tremendous amount of energy to the system, which can be both a help and a hindrance to this process. The gravitational forces can stir up the disk, encouraging more frequent collisions that help small moonlets grow. Yet, that same gravitational turbulence can also be destructive, pulling nascent moons apart or hurling them out of the system entirely before they can fully form. The resulting family of moons would likely be a diverse and strange collection. Instead of a few large, stable satellites like those orbiting Jupiter, this planet might be accompanied by a swarm of smaller, asteroid-like moonlets, or perhaps a single, large moon that managed to form in a stable orbital niche, a tranquil island in the gravitational storm. The potential for such a moon to itself become a habitable world, orbiting a planet that orbits two suns, is a thrilling prospect that pushes the boundaries of where we might one day find life. Ultimately, this dusty Tatooine world is more than just a celestial curiosity. It is a dynamic laboratory that challenges our understanding of planetary formation in the most extreme environments. It demonstrates that planet building is a resilient and adaptable process, capable of creating complex, multi-layered systems even under the duress of multiple gravitational masters. The persistent dust disk shows that the late stages of planetary system evolution can be far more active and messy than we once assumed, with materials continually being ground down, replenished, and reshaped over billions of years. As we continue to discover more of these binary systems, each one teaches us something new about the delicate balance of forces that can create a stable, long-lasting planetary family. This particular world, with its brilliant double sunsets filtered through a perpetual, glittering haze of cosmic dust, stands as a stunning testament to the universe's boundless creativity, crafting wonders that blend the familiar with the utterly alien. Deep in the heart of our own galaxy, hidden behind thick veils of interstellar dust, lies a mystery woven into the very fabric of space around the supermassive black hole. For decades, radio astronomers have been mapping this chaotic central region, and they've uncovered something that defies easy classification. Hundreds of long, slender, and perfectly straight magnetic filaments, some stretching up to 150 light-years in length. Picture these cosmic structures as if they were immense threads, delicately suspended in the void, all aligned in the same direction like streaks of rain caught in a street lamp's glow. They don't emit visible light or X-rays. They only reveal themselves through the synchrotron radiation they produce, a specific type of radio wave generated by high-energy electrons spiraling at near light speed along powerful magnetic field lines. Their sheer uniformity and organized arrangement is what makes them so bizarre, standing in stark contrast to the otherwise turbulent and explosive environment of the galactic center. The leading hypothesis for their origin connects them directly to the dormant titan at the galaxy's core, Sagittarius, a star. While our central black hole is relatively quiet today, there is compelling evidence that it experienced a period of tremendous activity in the relatively recent past, perhaps just a few million years ago. During such an active phase, the black hole's accretion disk would have been a raging inferno, and it could have launched colossal jets of plasma and energy, or generated massive outflows that surged outward into the surrounding medium. Theorists suggest that these outflows, as they interacted with the existing chaotic magnetic fields and molecular clouds in the galactic center, could have stretched and combed the magnetic field lines, much like combing a head of messy hair into straight, parallel strands. In this scenario, the filaments are the fossilized remnants of that immense energy release, a permanent record of a past eruption frozen in the magnetic architecture of the region. The high-energy electrons that cause the radio glow could be continuously re-energized by shocks within this magnetized plasma, or they could be cosmic rays from nearby supernova remnants that have become trapped, channeled along these magnetic highways like cars on a freeway. However, a newer and equally compelling theory has emerged, one that paints an even more dynamic picture. This idea posits that the filaments are not merely passive relics, but are actively involved in a vast cosmic-scale circuit. The theory suggests that the supermassive black hole during its past outbursts might have acted as a colossal battery, driving a powerful electrical current through the surrounding plasma. The filaments, in this view, could be the visible manifestation of these cosmic wires' immense, twisting bundles of magnetic flux that carry current across light years. The synchrotron radiation we detect would then be a direct result of this current flow. This would explain their remarkable straightness and coherence, as the magnetic fields are tightly wound and self-pinning, holding their structure against the disruptive forces of the interstellar medium. It also provides a potential explanation for why some filaments appear to be connected to pockets of young, massive stars. The same energetic processes that created the filaments could have triggered episodes of star formation, or the stellar winds from these new stars could be interacting with and illuminating the pre-existing magnetic structures. The true complexity of this system was further unveiled with the incredible resolution of the Mercator radio telescope in South Africa. Its recent surveys didn't just find more of the known vertical filaments. It revealed a population of shorter, younger-looking filaments that are oriented at different angles, and even a spectacular, bubble-like structure that seems to be interacting with them. This suggests that the story is not a single, simple event, but a layered history of multiple outbursts from the central black hole. Each period of activity may have combed the magnetic fields in a slightly different direction, creating overlapping sets of filaments that trace the history of the galaxy's core like rings in a tree trunk. Furthermore, the interaction of these magnetic threads with other objects, such as molecular clouds and stellar winds, creates localized bright spots and kinks, showing that they are not static museum pieces but dynamic elements in an ongoing cosmic drama. Studying these filaments is like doing galactic archaeology. By carefully mapping their lengths, orientations, and polarizations, astronomers can piece together a timeline of the violent energetic events that have shaped the inner galaxy over millions of years, offering a unique window into the life cycle of our supermassive black hole and its profound influence on its environment. While our runaway pulsar was a cosmic cannonball fired from a supernova, that is far from the only way the universe can launch a projectile. Imagine a star not as a dense stellar corpse, but a brilliant, living sun, hurtling through the intergalactic void at a speed so tremendous it is actively escaping the gravitational pull of our entire galaxy. This isn't science fiction. This is the reality of a hypervelocity star, and one particular celestial fugitive, known as L2, has a backstory more dramatic than any blockbuster. Its trajectory points to a stunning conclusion. This star is not a native of the Milky Way. It is an interloper, a visitor from a neighboring galaxy, and its incredible journey began with a close encounter with one of the most terrifying objects in the cosmos. The key to unraveling this mystery lies in tracing the star's path backwards through time. By meticulously measuring its velocity and position, astronomers were able to project its orbit millions of years into the past. Instead of originating from the bustling center of our own galaxy, the path led them outwards towards one of the Milky Way's small satellite galaxies, the Large Magellanic Cloud. This was a monumental discovery. It meant that L2 was not just any fast-moving star. It was the first clear case of a stellar immigrant, a body that had been ejected from another galaxy entirely and was now passing through our own cosmic neighborhood on its way out into the great, dark emptiness between galaxies. The sheer energy required to accomplish this is almost beyond comprehension. To fling a star out of a galaxy, you need a gravitational slingshot of unimaginable power. The most plausible engine for this stellar catapult is a dramatic and violent dance with a supermassive black hole. While the Large Magellanic Cloud is smaller than our Milky Way, it is thought to potentially host its own central supermassive black hole. The scenario that likely created L2 is known as the Hill's mechanism, a theoretical process that involves a binary star system venturing too close to such a gravitational monster. Picture two stars locked in a mutual orbit, swinging perilously close to the black hole's event horizon. The intense and uneven gravitational forces at play can violently disrupt the binary pair. In a gravitational sleight of hand, one of the stars can be captured into a tight orbit around the black hole, while its companion is whipped around like a stone from a sling and sent flying away at a significant fraction of the speed of light. This isn't just a gentle nudge, it's a cosmic cannon shot where the gravitational potential energy of the black hole is converted directly into the kinetic energy of the escaping star. The speed attained in such an event is truly staggering. L2 is racing through space at over 1.5 million miles per hour, a velocity so high that the Milky Way's collective gravity is insufficient to ever recapture it. It is on a one-way trip to intergalactic space, destined to drift alone through the cold, vast voids between galaxies for billions of years. Its future is a solitary one, a perpetual journey through darkness where the lights of other galaxies will slowly fade into the distance. This star will never again be part of a galactic disk, never witness the birth of new stars in a vibrant nebula, and will eventually burn out in profound isolation. The discovery of L2 does more than just add a fascinating object to our catalogues. It provides a unique and powerful test for our theories of galactic dynamics and the environments around supermassive black holes. Confirming that it came from the Large Magellanic Cloud implies that this smaller galaxy must have a sufficiently massive and compact central object to have powered such an ejection. It gives astronomers a new way to probe the conditions in other galaxies, using these hypervelocity runaways as tracers of violent events we cannot directly observe. Furthermore, the existence of such intergalactic travelers suggests that the space between galaxies may not be entirely empty, but could be sprinkled with these lonely, speeding suns, castaways from gravitational dramas that unfolded long ago and far away. Each one is a silent witness to the immense and often violent forces that shape the cosmos, reminding us that even something as seemingly permanent as a star can become a wanderer, set on an eternal path by a fleeting moment of catastrophic gravity. Now, let's turn from the violent dynamics of runaway stars and galactic centers to a sight of breathtaking celestial artistry, a nebula so intricate and visually stunning it has earned the name Dragon's Egg. Nestled within the cosmic tapestry, this glowing cloud of gas and dust presents a beautiful, almost organic form, its delicate shells and intricate filaments looking like the scales of some mythical cosmic serpent. But its serene beauty is deceptive. This nebula is the product of one of the most ferocious and short-lived types of stars in the universe, a Wolf-Rayet star, and its very structure is a diary of stellar violence and creative destruction written across light years of space. At the heart of this luminous nebula lies the true architect of this spectacle, a Wolf-Rayet star. These are not ordinary stars. They represent a brief, final, and intensely violent phase in the life of the most massive stars, those born with over 20 times the mass of our Sun. Having burned through their hydrogen fuel in just a few million years, a blink of an eye in cosmic terms, their cores have begun fusing heavier and heavier elements. This frantic nuclear activity generates a phenomenal amount of energy which the star cannot contain. The result is a constant hurricane force outflow of its own atmosphere. A Wolf-Rayet star is essentially tearing itself apart, shedding entire suns worth of mass in a relatively short period. The stellar wind it blows isn't a gentle breeze, it's a supersonic gale of charged particles racing outward at speeds of several million miles per hour. This relentless, powerful wind is the sculpting tool that carves the surrounding interstellar material, blowing enormous bubbles and shaping the complex structures we see as the Dragon's Egg Nebula. The process that forms the nebula's intricate shape is a dynamic and layered story. It begins with the star's earlier life as a red supergiant. During that more sedate phase, the star puffed out its outer layers in a slower, denser wind, creating a vast, diffuse shell of gas around itself. Then, when the star transitioned into its hyperactive Wolf-Rayet phase, the new, incredibly fast wind from the star's exposed core slammed into that pre-existing, slower-moving shell of material. The collision is titanic. The fast wind plows into the slower gas, compressing it, heating it to extreme temperatures, and sweeping it up into the intricate, glowing walls and filaments that define the nebula. This creates a classic wind-blown bubble structure, but the details, the delicate ripples, the sharp-edged ridges, the seemingly braided filaments, tell a more nuanced tale. They hint at instabilities in the colliding flows, areas where the shock front fragments and curls, much like cream swirling in a cup of coffee. The nebula isn't a static sculpture, it's a snapshot of an ongoing physical process, a moment frozen in an epic struggle between the star's outgoing fury and the resilience of its own cast-off envelope. What makes the Dragon's Egg glow with such vivid colors is a fascinating interplay of atomic physics and intense radiation. The central Wolf-Rayet star is not just windy, it is also unbelievably hot, with a surface temperature often exceeding 100,000 degrees Celsius. It bathes the surrounding nebula in a flood of high-energy ultraviolet photons. When this intense radiation strikes atoms in the nebula gas, it has enough energy to rip electrons right off them, a process called ionization. Later, when free electrons recombine with these ionized atoms, they release energy in the form of light. Each different chemical element emits light at specific characteristic colors or wavelengths. The strong blue-green glow often seen in images of such nebulae comes from doubly ionized oxygen, while red hues frequently indicate emission from hydrogen and nitrogen. The particular palette of the Dragon's Egg is therefore a direct chemical fingerprint of its composition, revealing the elements that were forged in the star's core and then ejected into space by its powerful winds. We are quite literally seeing the star's own nuclear waste painted across the cosmos by the star's brilliant, energizing light. The existence of this beautiful object, however, is tragically fleeting. A Wolf-Rayet star is living on borrowed time. It is in the final act of its life, mere thousands of years away from its ultimate fate, a core collapse supernova explosion. The Dragon's Egg Nebula is the star's final masterpiece, a last burst of creative output before the ultimate act of destruction. When the star's core finally runs out of fuel and collapses, the resulting supernova blast wave will overtake the nebula at an incredible speed. In a cosmic instant, the delicate structures painstakingly sculpted over millennia will be obliterated. their material violently mixed back into the interstellar medium. Yet, this destruction is also a new beginning. The supernova will seed the surrounding space with a fresh wave of heavy elements, the oxygen, carbon, iron, and silicon forged in the star's final moments. This enriched material will one day become part of new molecular clouds, new stars, and perhaps even new planetary systems. The dragon's egg, in all its transient beauty, is therefore a profound reminder of the cycle of cosmic life, a place where the death throes of a giant star create both a work of breathtaking art and the raw ingredients for future worlds. And just when we thought we'd encountered every form of cosmic chaos, the universe presented us with a signal that repeats with the precision of a metronome. From the heart of a distant galaxy, astronomers have detected a series of fast radio bursts, or FRB intense, millisecond-long flashes of radio waves that release as much energy as the sun does in 3 entire days. These events are, by their nature, famously fleeting and unpredictable except for this one. This specific source, designated FRB 180916, does something no other FRB had done when it was discovered. It bursts on a schedule. For 4 days, it remains completely silent. Then, for roughly 12 hours, it springs to life, firing off multiple bursts in a frantic, energetic window. After that, it falls silent again for another 4 days, only to resume its activity exactly on time. This cycle repeats every 16.35 days with a regularity that is as baffling as it is precise, a celestial clock ticking away in the depths of interstellar space. Unraveling the mystery of this clockwork repeater leads us directly to the most extreme and magnetically charged objects in the universe, neutron stars. These are the collapsed, ultra-dense cores of massive stars that died in supernova explosions, and they are the leading suspects for producing FRBs. One compelling theory suggests we are witnessing the dramatic interplay between a highly magnetized neutron star, a magnetar, and a companion star locked in a close orbital dance. In this scenario, the magnetar is tilted or precessing, meaning its rotation axis slowly wobbles like a spinning top winding down. As it precesses, its incredibly powerful magnetic poles, the regions from which these intense radio beams are likely emitted, sweep across the sky. For those 12 active hours in the cycle, one of these poles is pointed directly at Earth, and we see a flash every time a burst is emitted. Then, as the wobble continues, the beam points away from us for the next 4 days, and the signal vanishes from our view. This precession provides a natural, mechanical explanation for the periodic on and off behavior, a slow cosmic nodding that brings the beam in and out of our line of sight. But the presence of a companion star adds another layer of brilliant complexity to this model. The 16-day cycle could simply be the neutron star's orbital period around a massive partner. Imagine the magnetar on a long, elliptical path around a giant star. For the majority of its orbit, it is too far away for any significant interaction. But when it swings close to its companion, it plows through the dense, extended atmosphere of the larger star, or through a thick disk of material surrounding it. This close passage could trigger a cataclysm. The immense gravitational and magnetic forces at work could rip material from the companion star, causing it to rain down onto the neutron star's surface. Alternatively, the sudden immersion in a dense plasma could trigger a reconnection event in the magnetar's own field, a sudden and violent snapping of magnetic field lines that releases a colossal amount of energy, powering the radio bursts we see. In this model, the active window corresponds to this perilous close approach, the only time the environment is turbulent enough to trigger the eruptions, creating a predictable season of cosmic storms. The sheer, raw power required for an FRB is staggering, and the leading mechanism to generate it is as exotic as the objects themselves. The primary suspect is a phenomenon known as magnetic reconnection. Picture the magnetar's field as a convoluted web of immensely powerful rubber bands, twisted and stretched to their breaking point. when the stress becomes too great, perhaps from a starquake cracking the star's solid crust or from the influx of new material from a companion, the magnetic field lines can suddenly snap and reconfigure themselves. In that instant, a catastrophic amount of magnetic energy is converted into a blast of radiation and a firestorm of accelerated particles. This creates a shock wave that plows through the surrounding magnetosphere, and as electrons are whipped around by the magnetic fields at nearly the speed of light, they emit a coherent, laser-like beam of radio waves in a process called synchrotron maser emission. This beam is so focused and energetic that when it sweeps past Earth, it stands out dramatically against the quiet radio background of the cosmos, appearing as a brilliant extragalactic flash. The profound implications of this repeating patterned signal extend far beyond simply adding a new object to the celestial zoo. This regularity provides astronomers with something they have always craved when studying FRB's predictability. Instead of blindly staring at the sky hoping to catch a one-off event, they can now point the world's most powerful radio telescopes, like the CHIME array in Canada or the Deep Space Network on Earth, at this specific location, knowing precisely when the source will be active. This allows for coordinated, multi-wavelength observation campaigns. As the radio bursts arrive, other telescopes can simultaneously search for X-rays, gamma rays, or optical light from the same event, hoping to catch a glimpse of the engine at work. A correlated X-ray flash, for instance, would be a smoking gun, strongly supporting the magnetar model and giving us a direct probe of the violent physics occurring on the object's surface. This predictable repeater has become a Rosetta Stone for FRB science, a key that is helping us decode the language of these mysterious signals and finally understand their place in the dynamic story of our universe. Just when we thought we'd seen every possible way a solar system could arrange itself, astronomers found a world that seems to be breaking a fundamental rule of cosmic traffic. In a distant star system, there is a planet that moves in what can only be described as reverse gear, orbiting its star in the exact opposite direction to the star's own spin. This is a retrograde orbit, and it's as bizarre as watching a car drive the wrong way around a roundabout at high speed while everything else moves in perfect, orderly harmony. For a long time, we assumed that planets naturally form from a spinning disk of gas and dust that rotates in the same direction as the young star at its center, leading to a system where all the planets orbit in a neat, prograde fashion, much like the planets in our own solar system. The discovery of a backwards planet shatters that assumption and points to a history of incredible gravitational violence, a dramatic event in the system's past that literally flipped a world's path through space. The existence of such a planet implies a past filled with gravitational turmoil, and the most likely culprit is a scenario known as planetary scattering. Imagine a young solar system that was once more crowded, with multiple giant planets forming close to their star. In this densely packed environment, the delicate gravitational balance is inherently unstable. Over millions of years, the subtle tugs between these massive worlds can accumulate, perturbing their orbits until two of them have a close encounter. This isn't a collision, but a gravitational slingshot. As one planet swings perilously close to another, their mutual gravity acts like a cosmic catapult. One planet might be flung inward toward the star, while the other is ejected outward, or in some cases, one can be sent into a wildly inclined and even reversed orbit. The interaction is so violent that it can reorient the planet's entire orbital plane by over 90 degrees, effectively turning its path upside down. This process doesn't just create a backwards orbit, it often leaves the planet on a highly elongated, eccentric path, a lasting scar from the gravitational showdown that reshaped the system. Another compelling explanation involves an intruder from outside the system, a stellar flyby. Our solar system feels like an isolated island, but many stars are born in dense clusters where close encounters between sibling stars are relatively common in their youth. Picture another star, perhaps a rogue wanderer, passing a little too close to this planetary system. Although the stars themselves would not collide, the gravitational influence of the intruding star as it swings by would be immense. It would act like a colossal hand reaching into the clockwork, violently disturbing the orbits of any planets in the system. The outermost planets would feel this influence most strongly. A gas giant minding its own business in the outer reaches could have its orbit severely tilted or even completely reversed by the gravitational pull of the passing star. This would be a singular, catastrophic event, a brief period of cosmic chaos that leaves behind a permanently scrambled system, with at least one planet orbiting backwards as a permanent testament to the day a stranger came to town. Of course, there are more gradual theories, such as the quasi mechanism, a complex gravitational dance that can occur in a system with multiple large planets. In this scenario, the gravitational tug of war between an inner planet and a distant, massive companion, like another giant planet or a binary star, can slowly, over eons, pump up the inner planet's orbital inclination. Its orbit can evolve from flat to highly tilted, and in some extreme cases, this oscillation can flip the orbit all the way past 90 degrees, making it retrograde. It's a slower, more subtle form of gravitational engineering compared to the sudden violence of scattering or a flyby, but it is no less effective at producing a backwards world. The discovery of these retrograde planets forces a major shift in our perspective on planetary system architecture. It tells us that the neat, orderly model of planet formation is just one possible outcome. Many systems, perhaps even the majority, may undergo a period of dynamic instability in their youth, a turbulent adolescence that reshuffles planets, ejects some, and sends others into bizarre and unexpected orbits. This realization expands the definition of a normal solar system and suggests that our own placid, well-ordered cosmic neighborhood might be the exception rather than the rule. The backwards planet is a powerful reminder that the history of a solar system is written in the orbital paths of its worlds, and sometimes that history is a story of catastrophe and upheaval. Yet another ghost has appeared on our cosmic maps, this time etched not in radio waves or visible light, but in the most energetic form of radiation the universe can produce. Scattered across the sky, astronomers have found a series of colossal, perfectly circular rings of gamma-ray emission, structures so enormous they dwarf entire galaxies and so mysterious that their origin remains one of the most compelling puzzles in high-energy astrophysics. These are the Fermi bubbles, extensions of a phenomenon we see in our own galaxy, but on a scale that challenges our understanding of galactic power. These titanic, hourglass-shaped structures balloon out from the Milky Way's core, stretching for 50,000 light-years far above and below the galactic plane. They are filled with ultra-hot, magnetized gas that glows fiercely in gamma rays, and their very existence points to a cataclysmic, ancient eruption from the heart of our galaxy, an event of almost unimaginable violence that occurred millions of years ago. The leading theory for the creation of our own Fermi bubbles points directly to the supermassive black hole, Sagittarius, a star, though a period of intense activity long before recorded history. This was not a quiet nibbling on passing gas clouds, but a voracious feast. We believe the black hole underwent an explosive outburst, possibly triggered by the infall of an entire star or a massive gas cloud. During this active phase, it would have devoured matter at a tremendous rate, and in the process, it could have launched two colossal jets of energetic particles, shooting out in opposite directions perpendicular to the galactic disk. Alternatively, the energy might have been released in a more spherical, yet still incredibly powerful, outflow of winds from the hot accretion disk. In either case, the result was a pair of opposing shock waves that blasted outward, plowing through the halo of thin gas that surrounds our galaxy. These shocks swept up and compressed the existing material, energizing it and creating the vast, bubble-like structures we observe today. They are, in essence, the fading scars of a galactic-scale temper tantrum from our central black hole, a relic of a time when the Milky Way's heart was anything but quiet. But the mystery deepens considerably when we look beyond our own galaxy and find similar, and sometimes even larger, gamma-ray circles in the depths of intergalactic space. These are not associated with any obvious central galaxy or active galactic nucleus, and their immense size, often spanning hundreds of thousands of light-years, makes them incredibly difficult to explain. The first and most obvious suspects, supernova remnants, are simply not up to the task. A typical supernova remnant might be a few dozen light-years across. These gamma-ray circles are thousands of times larger. The collective energy from multiple supernova in a starburst galaxy could, in theory, blow a giant bubble, but the energy required to create structures of this scale and luminosity in gamma rays is so staggering that it pushes the limits of what even the most intense star-forming galaxies are capable of producing. The circles are too big, too symmetrical, and often too isolated to be easily explained by known stellar processes. This has forced astronomers to consider more exotic and powerful engines. One compelling hypothesis revisits the idea of active galactic nuclei, but on a truly epic scale. Perhaps these circles are the remnants of ghost and supermassive black holes in distant galaxies that had a single colossal eruption millions of years ago and have since fallen silent. The jets or winds from that ancient event would have inflated these giant bubbles, which have persisted long after the central engine shut down. We are seeing the fossilized energy from an eruption that has since faded from view, a cosmic aftermath frozen in time. Another, more speculative idea involves the dark matter that permeates the cosmos. Could these circles be the indirect signature of dark matter particles annihilating with one another? If certain theoretical particles of dark matter were to collide, they would annihilate in a flash of energy, potentially producing gamma rays. If such an event were triggered in a particularly dense clump of dark matter, it could, in principle, create a spherical outburst of radiation. While this is a tantalizing possibility, the sheer energy and precise morphology of the circles don't perfectly match most dark matter annihilation models, leaving this as a fascinating but unproven avenue of investigation. The very persistence of these gamma-ray circles in the data presents a fundamental challenge. They are not easily explained by any one known phenomenon, which suggests we might be seeing the result of a combination of forces or an entirely new class of event. Some theorists have proposed they could be the remnants of a binary black hole merger, where the gravitational wave recoil from two merging supermassive black holes ejected them from their galactic core, and their final, frantic act of accretion during the merger blew one last, immense bubble into intergalactic space. Others wonder if they are the result of a quasar remnant, the dying breath of a once brilliant quasar. What makes these objects so scientifically valuable is that they are not just mysterious, they are immense high-energy laboratories. By studying their spectrum and structure, we can probe the density and magnetic field strength of the truly intergalactic medium, a region of space that is notoriously difficult to observe. These ghostly circles, glowing with the universe's most violent light, are therefore more than just cosmic curiosities. They are immense signposts pointing toward gaps in our understanding of galactic evolution, black hole behavior, and the very nature of the space between galaxies. They remind us that even with the most energetic phenomena, the universe still holds onto its most dramatic secrets. Now, let's turn our gaze back toward our own galactic neighborhood and a star that pulled off one of the most enigmatic disappearing acts ever witnessed. In the constellation Cygnus, a fairly ordinary star, catalogued as KIC 8462852, but now famously known as Boyajian star, began behaving in a way that baffled every astronomer who looked at it. Over a period of several years, its light, as measured by the Kepler Space Telescope, didn't just dip in the regular, predictable way of a planet transit. Instead, it plummeted, with its brightness dropping by staggering amounts, up to 22% at times, in chaotic, asymmetrical dips that lasted for days or even weeks. The star became a global sensation, a cosmic puzzle that seemed to defy all natural explanation. But the real twist came later, after the initial furor had died down. The star did something many had stopped expecting. It began to fade again, dramatically, in an event nicknamed the Elsie dip, proving that whatever was causing the strangeness was not a one-time fluke, but an ongoing, active process. This star wasn't just weird, it was persistently, mysteriously weird, dimming and brightening on its own incomprehensible schedule. The initial, dramatic dimming events were so unusual they forced scientists to throw out the standard playbook. A planet, even a giant one, would only block about 1% of a sun-like star's light, and it would do so with a smooth, symmetrical, and perfectly periodic curve. What Kepler observed was nothing like that. The dips were deep, jagged, and completely aperiodic, coming at irregular intervals and with wildly different profiles. It was as if something was passing in front of the star that was not a simple, solid sphere, but an incredibly complex, clumpy, and dynamic swarm of objects. This immediately ruled out simple planetary transits and sent researchers scrambling for more exotic explanations that could account for such an intricate and variable shadow. The leading natural explanation, and the one that has gained the most traction, involves a family of comets. The theory suggests that Boyajian's star is being orbited by a vast swarm of exocomets, perhaps the remnants of a giant icy body that broke apart in the recent cosmic past. As these countless comets travel on their long, elliptical orbits, they would release enormous clouds of dust and gas, their glowing tails stretching out for millions of miles. If a tightly packed cluster of these comets, all trailing immense amounts of debris, were to pass in front of the star from our vantage point, they could create the kind of complex, multi-peak dimming patterns we observe. The slow, long-term dimming of the star over the past century, as seen in archival photographic plates, also supports this idea, as it could be caused by a slowly dispersing, giant cloud of fine dust from a past cataclysmic collision within the swarm, a cloud that is only now beginning to clear and allow the star to brighten once more. However, the comet swarm hypothesis, while compelling, is not without its own significant challenges. To create the deepest observed dips, the amount of dust required is truly colossal, pushing the limits of what we believe is physically possible for a single family of comets. The fine dust also presents a problem. Radiation pressure from the star itself should quickly blow such small particles away, clearing the cloud on a relatively short timescale. For the dust to persist and create multiple dimming events over years, there must be a continuous and massive source replenishing it, a factory of dust production that is difficult to sustain. This has led some researchers to explore even more exotic natural possibilities, such as the aftermath of a planetary collision that littered the system with fine debris or intrinsic variability within the star itself. Perhaps the star is going through a period of immense magnetic activity, with huge, dark star spots like sunspots, but on a gargantuan scale, coalescing on its surface and rotating in and out of view. While star spots can cause dimming, they typically produce more regular, periodic variations, not the sharp, dramatic drops seen in Boyajian's star, making this a less likely, though still considered, explanation. Of course, the very extremity of the observations is what launched 1,000 headlines and captivated the public imagination: the alien megastructure hypothesis. The idea, first suggested by astronomer Jason Wright, is that we might be witnessing the construction of a Dyson sphere, or more likely, a Dyson swarm, a vast collection of energy collecting satellites or habitats orbiting a star to harness its total power output. From our distant vantage point, a partially completed swarm of such megastructures, with their irregular shapes and orientations, would indeed block the star's light in chaotic, unpredictable, and deeply asymmetric ways, creating a light curve that looks remarkably similar to what we've recorded. It's a hypothesis that is as thrilling as it is profound, suggesting that we may have stumbled upon the first tangible evidence of a civilization whose engineering capabilities dwarf our own. Yet, for all its science fiction appeal, the scientific community approaches the megastructure idea with extreme caution, and for good reason. The first and most important rule of science is to seek natural explanations before invoking the extraordinary. More recent and detailed observations have provided strong evidence against the alien hypothesis. When the star dimmed during the ELSI event, astronomers used the Los Cumbres Observatory Global Telescope Network to immediately study the star's light across different colors or wavelengths. They found that the star dimmed more significantly in blue light than in red light. This is a classic signature of dust. Small dust particles scatter and absorb blue light more effectively than red light, so when a dusty cloud passes in front of a star, the star appears redder as it fades. A solid object like a planet or an alien megastructure would block all wavelengths of light equally, causing a uniform dimming across the color spectrum. The fact that the dimming is wavelength dependent is a nearly definitive nail in the coffin for the solid megastructure idea, strongly pointing back toward a natural, dusty cause. The ongoing saga of Boyajian star has fundamentally changed how we do astronomy. It taught us the immense value of archival data, as century-old photographic plates provided the crucial clue of the long-term dimming. It demonstrated the power of citizen science, as the initial discovery was made by volunteers in the Planet Hunters project sifting through public Kepler data. And it has pioneered a new model of rapid response astronomy, where networks of telescopes around the world stand ready to spring into action at a moment's notice to catch the next dimming event in real time. This star is more than just a single cosmic oddity. It has become a catalyst pushing us to develop new tools, new collaborations, and a new level of vigilance as we scan the heavens. It serves as a powerful reminder that sometimes the most important discoveries are not the answers we find, but the new and better questions we are forced to ask. The mystery of why this star flickers is not yet fully solved, but the relentless pursuit of its secret continues to illuminate the path of scientific discovery itself. After a star like our Sun exhausts its nuclear fuel, it doesn't just fade away. It goes through a spectacular, though ultimately destructive, transformation, swelling into a red giant that engulfs the inner planets before shedding its outer layers and collapsing down into an Earth-sized ember of ultra-dense matter, a white dwarf. These stellar remnants are incredibly hot and, according to theory, should possess atmospheres of almost pure hydrogen or helium, because any heavier elements, what astronomers call metals, should quickly sink into their intense gravitational fields, vanishing from view in a relatively short cosmic time. That's why the discovery of certain white dwarfs with clear, undeniable metal signatures in their light spectra is so startling. It means we are catching these cosmic tombstones in the act. We are witnessing evidence of a recent and violent cosmic meal. These are the cannibal white dwarfs, stars that, in their death throes, have consumed the very planets they once nurtured. The evidence for this planetary digestion is written in the star's light. Astronomers use a technique called spectroscopy, which splits the light from a star into a rainbow-like spectrum. Dark lines appearing at specific wavelengths in this spectrum act as unique chemical fingerprints, revealing which elements are present in the star's atmosphere. When these lines correspond to elements like iron, silicon, calcium, and oxygen, the fundamental building blocks of rocky worlds like Earth, it presents a profound puzzle. These heavy elements simply cannot be manufactured by the white dwarf itself. They are foreign contaminants, pollutants that must have been added from an external source after the star's transformation was complete. The most logical explanation is that the white dwarf's immense gravity has torn apart and drawn in material from its surrounding system. the scattered remnants of planets, asteroids, and comets that survived the star's red giant phase. We are essentially analyzing the chemical makeup of a devoured world by studying the atmosphere of the star that consumed it. This process of accretion is a violent and final chapter for any surviving planetary bodies. After the star's red giant phase subsides, the white dwarf that remains is surrounded by a chaotic debris disk, a cosmic graveyard of planetary wreckage. This disk is composed of everything from dwarf planets to vast collections of asteroids, all orbiting in a destabilized environment. The gravitational interactions within this disk, or the subtle influence of surviving outer planets, can perturb the orbits of these smaller bodies, sending them on a collision course with the central star. As a large asteroid or a small planetesimal ventures too close, the white dwarf's powerful tidal forces, the same kind of forces our moon exerts on Earth's oceans, but amplified to an unimaginable degree, overwhelm the object's own gravitational cohesion. The rocky body is literally ripped apart, shredded into a cloud of dust and gas in an event called tidal disruption. This debris then forms a glowing, hot accretion disk around the white dwarf, and over thousands of years, this material slowly spirals inward, eventually raining down onto the star's surface and imprinting its metallic signature onto the otherwise pristine atmosphere. The profound value of these cannibal stars is that they allow us to perform a kind of cosmic autopsy, determining the precise composition of planets that once orbited far-off stars. By carefully measuring the ratios of different elements polluting a white dwarf's atmosphere, planetary scientists can reconstruct what the consumed object was made of. For instance, a high abundance of iron and nickel relative to silicon and oxygen might suggest the accreted material came from the core of a differentiated body, a planet that, like Earth, had separated into a dense metallic core and a rocky mantle. Conversely, a mix that looks more like common chondritic meteorites, the raw material of the early solar system, could point to the consumption of a more primitive asteroid that never underwent this planetary differentiation. This gives us direct, bulk compositional data for exoplanetary systems, a critical reality check for models of planet formation that we simply cannot get from any other observation method. It's as if the universe has provided us with a catalog of planetary ingredients, the crushed remains of alien worlds laid bare for our inspection. This grim fate has profound implications for the long-term future of our own solar system. In about 5 billion years, our sun will begin its own transformation into a red giant, swelling to a size that will almost certainly engulf and vaporize Mercury and Venus. The fate of Earth is less certain. It may be swallowed, or it may just barely escape incineration, left as a scorched, barren cinder orbiting a dying star. What is far more certain is the chaos that will ensue. The sun's mass loss as a red giant will destabilize the orbits of all the remaining planets, asteroids, and comets, likely triggering collisions and sending countless objects spiraling inward. The asteroid belt between Mars and Jupiter will become a shooting gallery, and many of these rocky bodies will ultimately be torn apart by the white dwarf sun's gravity, adding their metallic dust to its atmosphere. The discovery of these cannibal white dwarfs is therefore a direct glimpse into the ultimate destiny of our own planetary neighborhood, a stark and sobering reminder that even the most stable-looking solar systems are transient, destined to end in a final, violent feast as the central star breathes its last. Now imagine a delicate, luminous strand of cosmic jewels stretched across the dark velvet of interstellar space, a breathtaking alignment of stellar nurseries that astronomers have poetically named a string of pearls. This isn't a random scattering of stars, it's a perfect, sequential line of brilliant blue-white star-forming regions, each one a massive, glowing cloud of gas and dust where new suns are igniting in a chain reaction of creation. The existence of such a perfectly ordered structure reveals a universe where star birth can be orchestrated on a galactic scale, triggered by a single titanic event that sent a wave of energy rolling through the cosmos, turning quiet cosmic gas into a spectacular production line of new solar systems. The most likely architect of this celestial jewelry is a shockwave of almost unimaginable power, and the prime suspect is often the supermassive black hole lurking at the galaxy's heart. During a period of intense activity, when the black hole is consuming vast amounts of matter, it can release colossal jets of energy or generate immense outflows that blast outward from the galactic center. This eruption doesn't just travel through empty space, it slams into the much denser, quiescent reservoirs of hydrogen gas that fill the galactic disk. The collision is like a sonic boom on a cosmic scale. The leading edge of this outflow acts as a formidable shock front, a moving wall of immense pressure that plows into the gas. This sudden, violent compression is the trigger. It takes a cloud that was stable, if a bit tenuous, and squeezes it violently, increasing its density and gravity to the point where the cloud can no longer support itself against its own weight. It collapses, fragmenting into dense cores that rapidly heat up until nuclear fusion ignites in their hearts, lighting up the first pearl in the chain. As this shockwave continues its journey through the galaxy, it doesn't just stop after creating one stellar nursery. It keeps going, a relentless, expanding ripple of pressure traveling through the interstellar medium. The process is one of sequential triggering. The initial shockwave compresses the first giant molecular cloud it encounters, initiating a firestorm of star formation. But the story doesn't end there. The massive, hot, young stars born in that first pearl don't just sit quietly. They live fast and die young, and in their short lives, they flood their surroundings with intense ultraviolet radiation and powerful stellar winds. This output from the first generation of stars itself creates a secondary shockwave, a new bubble of high pressure that expands outwards and collides with the next suitable cloud of gas down the line. This new shock then triggers the next round of star formation, which in turn creates the next shockwave, and so on down the line. It's a domino effect of stellar birth, a self-propagating wave of creation that strings together one brilliant pearl after another, with each new cluster of stars lighting the fuse for the next. An alternative and equally dramatic origin story for these structures is a galactic collision. When two galaxies gravitationally intertwine in a slow, billion-year dance, their mutual tidal forces act like immense gravitational hands, ruthlessly squeezing the gas within them. This doesn't just create random chaos, it can funnel and compress vast streams of gas along precise lines, creating dense, linear structures within the newly merging system. Within these tidal tails of gas, the conditions become perfect for the same sequential triggering to occur. A cluster of stars forms in the densest knot, and its feedback drives a shock that ignites the next knot, creating a brilliant string of newborn star clusters that traces the very arc of the galactic interaction itself. This makes the string of pearls not just a beautiful phenomenon, but a fossilized record of a past cosmic crash, a luminous scar that shows where two galaxies touched and set the universe ablaze with new light. Observing one of these strings is like watching a time lapse of stellar evolution frozen in a single, magnificent structure. At the head of the line, you see the youngest, most embedded protostars, still swaddled in their thick, dusty cocoons and visible mainly in infrared light. As you move down the strand, the pearls show progressively more developed stellar clusters. The gas and dust around them is being blown away by the fierce radiation from the massive new stars, revealing brilliant, open clusters of blue giants. At the very end of the chain, you might find the oldest pearls, where the most massive stars have already exhausted their fuel and died in spectacular supernova, leaving behind expanding supernova remnants that themselves contribute to the shockwave, potentially triggering yet another cycle of star formation even farther out. This single, elegant structure therefore encapsulates the entire life cycle of stars, from their violent birth in compressed gas to their explosive death, all laid out in a perfect sequence for us to study. It demonstrates that star formation is not always a solitary, isolated event, but can be a communal, connected process where the birth of one generation directly paves the way for the next, weaving a necklace of light across the dark expanse of a galaxy. And just when we think we've mapped the life cycles of every type of star cluster, the universe throws us a curveball that rewrites the entire first chapter. In a galaxy far, far away, astronomers have discovered a celestial object that should not exist, a dense, blazingly bright, and incredibly massive cluster of young stars that looks, for all intents and purposes, like a newborn globular cluster. This discovery, a potential proto-globular cluster, strikes at the heart of a long-held assumption in astronomy. We've always thought of globular clusters as the ancient retirees of the galaxy, vast spherical swarms of hundreds of thousands of stars that are nearly as old as the universe itself, relics from a violent, formative epoch when galaxies were first assembling. They were thought to be a product of a unique, bygone era, a special kind of star formation that the modern, universe simply doesn't do anymore. Finding one in its infancy is like stumbling upon a living, breathing dinosaur hatchling. It suggests that the conditions for creating these cosmic fossils never actually went away, and that our understanding of their birth is fundamentally incomplete. The traditional story of a globular cluster is one of primordial origins. In the early, chaotic universe, vast, dense clouds of pristine gas, rich with the first heavy elements, collapsed under their own tremendous gravity. In these extreme environments, star formation wasn't a gentle, sporadic process. It was a frenzied, single burst of activity that created hundreds of thousands of stars all at once, packed into a relatively tiny volume of space. This ferocious burst of birth used up all the available gas in one go, leaving behind a gravitationally bound ball of stars that has been slowly orbiting its host galaxy ever since, its stars aging in lockstep for over 10 billion years. The key point is that this was a one-and-done event, a type of starburst that the universe seems to have outgrown. In today's more settled cosmic era, the giant molecular clouds that form stars are less massive, less dense, and tend to produce open clusters, looser, younger groupings that eventually drift apart over a few 100 million years. The conditions to make a single, bound cluster with the mass of a small galaxy were believed to be a thing of the past. This newly discovered object shatters that timeline. Observations from powerful telescopes like Hubble and the James Webb Space Telescope reveal a cluster of staggering youth. Its stars perhaps only a few million years old, yet already containing the mass of several million suns, all crammed into a region just a few dozen light years across. To put that density into perspective, if you were to place this cluster in our own galactic neighborhood, the night sky from a planet within it would be ablaze with tens of thousands of stars as bright as Venus, with many of them so close together that their solar systems might gravitationally interact. This isn't just a big young cluster, it has the specific mass, density, and structural signature of a classic globular cluster, but caught in the act of lighting up for the very first time. It is a cosmic anachronism, a modern object with ancient characteristics, forcing us to ask how such a dense, massive cluster could form in the contemporary universe. The leading theories for its existence point to environments of extreme cosmic violence that do, in fact, still exist today. One compelling scenario involves galactic collisions. When two gas-rich galaxies slam into each other, the resulting gravitational turbulence can compress enormous reservoirs of gas into incredibly dense, massive knots. These knots, subjected to immense pressure from the colliding galactic forces, can then undergo a cataclysmic burst of star formation, essentially replicating the conditions of the early universe and producing a single, monstrously large star cluster in one fell swoop. This object could be the direct result of such a recent, violent merger, a testament to the fact that while the universe on average is calmer, local conditions can still recreate its most ferocious early episodes. Another fascinating possibility is that this cluster is forming in the heart of a modern-day starburst galaxy, a region where the rate of star formation is so incredibly high that it defies belief. In these extreme environments, the sheer concentration of gas and the relentless triggering of new stars by supernova shockwaves could allow a cluster to accumulate mass at a rate and to a density that we once thought was impossible outside the universe's first few billion years. This suggests that the recipe for a globular cluster isn't lost. It just requires a specific, high-energy environment that can force a giant molecular cloud to collapse in on itself all at once, rather than fragmenting into many smaller clusters as it usually does. The discovery of this impossible protocluster fundamentally changes the narrative. It tells us that globular clusters are not merely fossils. They can be living entities born in the modern cosmos under the right, if extreme, circumstances. This expands the potential habitats for these dense stellar cities and suggests that our own Milky Way, if it experiences a significant gas-rich merger in the future, might yet give birth to a new generation of these ancient-seeming structures. From the deep silence of intergalactic space and the explosive deaths of stars, we now turn our attention to a cosmic symphony playing right in our own backyard. The Sun, our life-giving star, has long been a subject of intense study, but only recently have we learned to listen to its music. High above its visible surface, in the million-degree outer atmosphere known as the corona, astronomers have discovered immense arching structures called magnetic ropes. These are not physical cords, but tightly bundled tubes of magnetic field lines, channels of immense force that snake through the solar plasma, often serving as the precursor to the Sun's most violent outbursts. The truly mesmerizing part is that these colossal structures don't just sit in silence, they vibrate and oscillate, and when these vibrations are translated into sound, they produce an eerie, ethereal song, a chorus of low-frequency hums and waves that reveal the hidden dynamics of our star's most volatile region. The process of hearing this solar music is a fascinating feat of scientific translation. Space itself is a vacuum, so sound waves as we know them cannot travel from the Sun to Earth. Instead, scientists use a technique called coronal seismology. Powerful satellites like the Solar Dynamics Observatory don't have microphones. They have instruments that capture ultra-high definition, rapid-fire images of the Sun's atmosphere in various wavelengths of light. By meticulously tracking the movements of these glowing magnetic ropes over time, scientists can detect subtle, rhythmic oscillations, the ropes swaying, twisting, and expanding as if plucked by an invisible hand. These visual oscillations are then assigned corresponding sound frequencies, a process called sonification. A slow, gentle sway might become a deep, resonant cello note, while a rapid, high-frequency vibration could be translated into a shimmering chime. When played back, the result is a haunting, otherworldly choir, the Sun's magnetic field singing a song of its own turbulent energy. It's a direct auditory window into the forces that govern our star's behavior. This celestial music is far more than just a scientific curiosity. It is a powerful diagnostic tool that is helping to unravel one of the most enduring mysteries in solar physics, the problem of coronal heating. For decades, scientists have been baffled by a simple but profound question. Why is the Sun's corona, its outer atmosphere, so incredibly hot? The visible surface of the Sun, the photosphere, has a temperature of around 5,500 degrees Celsius. Yet, just a few thousand kilometers above, the corona routinely heats to between 1 and 3 million degrees. It's as if you walked away from a campfire and instead of getting colder, you stepped into a blast furnace. This defies all intuitive laws of thermodynamics. The vibrating magnetic ropes provide a crucial clue. The energy carried by these oscillations, a form of magnetohydrodynamic wave energy, is now believed to be a primary mechanism for transferring vast amounts of energy from the Sun's interior out into the corona. As the ropes vibrate and waves travel along them, their energy is dissipated into the surrounding plasma, effectively cooking it to multi-million-degree temperatures. By analyzing the specific frequencies and amplitudes of the songs, scientists can quantify how much energy is being pumped into the corona, turning an abstract mystery into a measurable physical process. Perhaps the most immediately practical application of this research lies in the burgeoning field of space weather prediction. These same magnetic ropes are often the very structures that, when they become over-twisted and unstable, trigger massive solar flares and coronal mass ejections explosions that can hurl billions of tons of charged particles toward Earth. These events have the potential to wreak havoc on our technology, damaging satellites, disrupting power grids, and posing radiation risks to astronauts. The key to prediction is understanding the tension within these ropes before they snap. The songs they sing act as a form of cosmic stress test. Just as the pitch of a guitar string rises as you tighten it, changes in the oscillation frequency of a magnetic rope can indicate that the magnetic field is becoming more tense, storing more energy, and nearing a breaking point. A sudden shift from a steady, low hum to a higher-pitched, more chaotic set of vibrations can be an early warning siren, signaling that a rope is under extreme stress and a flare is imminent. By learning to interpret these acoustic signatures, scientists are developing the ability to forecast solar storms with greater accuracy and lead time, potentially giving us crucial days to protect critical infrastructure. The study of these solar harmonies represents a beautiful convergence of observation, theory, and practical application. It transforms the sun from a distant, silent ball of fire into a dynamic, vibrating entity whose hidden forces are expressed in a language of waves and oscillations that we are only just learning to decipher. Each eerie tone and shifting rhythm is a data point in a grander understanding, helping us piece together the puzzle of our star's violent nature while also safeguarding our increasingly technological civilization. This celestial symphony, played on magnetic strings of unimaginable power, reminds us that even our own familiar sun holds profound secrets, waiting to be heard by those who know how to listen. And so, our journey through the cosmos's cabinet of curiosities comes to a close for now. From universe breaker galaxies that defy time itself to the silent, perfect rings of odd radio circles hanging in the void, these 30 discoveries are far more than a simple list of weird facts. They are a powerful, collective testament to a single, breathtaking truth. The universe is not just stranger than we imagine, it is stranger than we can imagine. Every time we build a new telescope, every time we point a new instrument at the heavens, we are not just filling in the blanks on an existing map. We are finding that the map itself is wrong, that there are entire new continents of reality we never knew existed, governed by rules we are only beginning to glimpse. This is the golden age of cosmic discovery, not because we are finding all the answers, but because we are being humbled by a flood of magnificent, beautiful, and utterly perplexing new questions. Think about the sheer range of wonders we've encountered. We've seen stars that pulse with a rhythmic heartbeat, black holes fleeing their galactic homes, and planets with skies filled with multiple suns. We've found invisible galaxies made almost entirely of dark matter, and then, in a stunning paradox, a galaxy that seems to have no dark matter at all. We've decoded the magnetic songs of our own sun and listened for the repeating signals from distant, hypermagnetized stellar corpses. Each one of these oddities is a crack in the facade of our understanding, a place where the light of a deeper, more complex reality is shining through. They remind us that our theories, no matter how elegant, are merely provisional sketches of a masterpiece that is infinitely more detailed and wildly more inventive. The cosmos is not a passive backdrop. It is an active, dynamic, and deeply creative force, constantly challenging us to think bigger, to question deeper, and to embrace the wonderful uncertainty of it all. This is why the work of astronomers and physicists is so vital. They are the cartographers of the unknown, patiently translating the faint whispers of light and radio waves into a language we can all begin to understand. Their discoveries ripple out, changing not just textbooks, but our very perception of our place in the grand scheme of things. We are living on a tiny, fragile world, orbiting an average star in a quiet suburb of a galaxy that is itself just one among trillions. And yet, with our curiosity and our ingenuity, we can reach out across the vastness of space and time to uncover secrets on a scale that dwarfs our everyday experience. It is a profoundly human endeavor, one that connects us all in a shared sense of wonder. Now we turn the conversation over to you. With 30 of the most bizarre and mind-bending space oddities laid out, which one captured your imagination the most? Was it the diamond world racing between its twin suns, the mysterious tumbling journey of Oumuamua, or the haunting great cold spot, a potential bruise from a collision with another universe? Let us know in the comments below. We love reading your thoughts and diving into these cosmic mysteries together. The adventure doesn't have to end here. If your appetite for the wonders of the cosmos has been whetted, make sure to subscribe and hit the notification bell. We are constantly exploring new frontiers and unraveling new enigmas, from the secrets of black holes to the search for life beyond Earth. Thank you for joining us on this incredible tour of the universe's greatest hits of weirdness. Keep looking up and never stop wondering.